Welcome to our journey through the full history of the universe. From the moment of the Big Bang to the far future, we'll explore the fascinating events that shaped the cosmos. Join us as we uncover the mysteries of space and time, revealing the incredible story of the universe. Our story begins with the Big Bang, the explosive event that gave birth to the universe. In an instant, all matter and energy were created, setting the stage for everything that would follow. Scientists have gathered compelling evidence for this theory, including the cosmic microwave background radiation, which offers a glimpse into the universe's earliest moments. Following the Big Bang, the universe went through a rapid inflation period, expanding faster than the speed of light. During this time, the fundamental particles that make up all matter were formed. Quarks combined to create protons and neutrons, and eventually the first atomic nuclei emerged. As the universe continued to cool, the first elements began to form through a process known as primordial nucleosynthesis. Hydrogen and helium, the simplest elements, became the building blocks for future stars and galaxies. These light elements spread throughout the cosmos, setting the stage for the next phase of cosmic evolution. The universe then entered a period known as the Dark Ages. During this time, there was no light as the first atoms had not yet formed. Eventually, the universe cooled enough for electrons to combine with protons, creating neutral hydrogen atoms. This led to the emission of the cosmic microwave background radiation, a crucial piece of evidence for the Big Bang theory. With the end of the Dark Ages, the first stars began to form. These early stars, known as population 3 stars, were massive and short-lived, playing a key role in creating heavier elements through nuclear fusion. The light from these stars marked the dawn of the first galaxies, which began to shape the structure of the universe. Galaxies, the massive systems of stars, gas, and dark matter, started to form and evolve. Over time, they merged and interacted, creating the diverse array of galaxies we observe today. Galaxy clusters, the largest structures in the universe, emerged from these interactions, forming the cosmic web that defines the large-scale structure of the universe. Dark matter, an invisible and mysterious substance, plays a crucial role in the formation and evolution of galaxies. While we cannot see dark matter directly, its gravitational effects are evident in the rotation of galaxies and the movement of galaxy clusters. Scientists continue to study dark matter, seeking to understand its nature and origins. The expansion of the universe is another key aspect of its history. Edwin Hubble's observations of distant galaxies revealed that the universe is expanding, with galaxies moving away from us at speeds proportional to their distance. More recently, we've discovered that this expansion is accelerating, driven by a mysterious force known as dark energy. Various theories suggest different outcomes, from the Big Freeze to the Big Crunch or the Big Rip. As we continue to explore the cosmos, we hope to uncover more answers about the ultimate destiny of the universe and our place within it. The observable universe refers to the portion of the entire universe that we can see and measure. It is limited by the speed of light and the age of the universe. Since light takes time to travel, we can only observe objects whose light has had enough time to reach us. Beyond the observable universe lies the entire universe, which is much larger and potentially infinite. We can't see or measure these distant regions because their light hasn't had enough time to reach us. This limitation creates a cosmic horizon, beyond which our knowledge is limited. The observable universe is estimated to be about 93 billion light-years in diameter. This vast expanse contains all the galaxies, stars, and other cosmic structures that we can study with our current technology. Despite its immense size, it represents only a small fraction of the entire universe. Understanding the difference between the observable universe and the entire universe is crucial for cosmology. It helps scientists frame their theories and models about the origins and evolution of the cosmos. By studying the observable universe, we can infer properties about the whole universe. Cosmic inflation, a rapid expansion shortly after the Big Bang, suggests that the entire universe is much larger than the observable portion. During this brief period, space expanded faster than the speed of light, pushing regions of the universe beyond our observational reach. The concept of the observable universe introduces the idea of a cosmic horizon, similar to an event horizon around a black hole. Just as we cannot see beyond a black hole's event horizon, we cannot observe beyond the cosmic horizon. This boundary continually expands as the universe ages. Different models of the universe, such as the flat, open, and closed models, impact our understanding of its size and shape. These models are based on measurements of the cosmic microwave background radiation, the distribution of galaxies, and other observations. The curvature of space also plays a role in defining the observable universe. If the universe is flat, parallel lines remain parallel, and the geometry is Euclidean. In a curved universe, the geometry would differ, potentially altering the observable horizon. Gravitational waves, ripples in space-time caused by massive cosmic events, offer a new way to explore the universe. By detecting these waves, scientists can gather information about regions beyond the observable universe, providing indirect evidence of what lies beyond. The universe's expansion rate, influenced by dark energy, affects our observable universe. As the expansion accelerates, more regions will move beyond our observational reach, making it even harder to study the entire universe. This acceleration complicates our quest to understand the cosmos. Some theories propose the existence of a multiverse, where our universe is just one of many. These parallel universes might have different physical laws and constants. While we can't observe these other universes directly, their existence could explain some of the mysteries of our own universe. The cosmic microwave background radiation is a crucial tool for studying the observable universe. It provides a snapshot of the universe when it was just 380,000 years old, offering insights into its early conditions and the distribution of matter and energy. Large-scale surveys of galaxies and cosmic structures help map the observable universe. Projects like the Sloan Digital Sky Survey have catalogued millions of galaxies, revealing patterns and structures that help us understand the universe's evolution. Advancements in technology, such as the development of more powerful telescopes and space observatories, continue to push the boundaries of the observable universe. These instruments allow us to peer deeper into space, revealing objects and phenomena previously unseen. By studying the observable universe, scientists hope to answer fundamental questions about the nature of the cosmos. Each discovery brings us closer to understanding the entire universe, even if it remains beyond our direct observational capabilities. Welcome to our journey through the full history of the universe. In this video, we'll explore the monumental events that have shaped the cosmos from its inception to its current state. Each section will delve into a specific era, providing a comprehensive understanding of the universe's evolution. We'll begin with an introduction to the universe, setting the stage for our exploration. Here, we'll define what the universe is and distinguish between the observable universe and the entire universe. This foundational knowledge will help us appreciate the scale and complexity of what we're about to uncover. Next, we'll dive into the Big Bang, the explosive event that marks the birth of the universe. We'll explore the evidence supporting this theory, the initial conditions, and the rapid inflation period that followed. Understanding these early moments is crucial to grasping how the universe began to take shape. Following the Big Bang, we'll discuss the formation of the first elements. Through a process known as primordial nucleosynthesis, hydrogen and helium emerged, laying the groundwork for future stars and galaxies. This section will highlight the significance of these light elements in cosmic history. After the formation of the first elements, we'll enter the era known as the Dark Ages. During this period, the universe was devoid of light until the first atoms formed. We'll examine the cosmic microwave background radiation, which provides a snapshot of the universe during this time. With the end of the Dark Ages, the first stars began to form. These population 3 stars were massive and short-lived, playing a pivotal role in creating heavier elements. This section will illuminate the birth of the first light sources in the universe and their impact on subsequent cosmic structures. The formation and evolution of galaxies come next. We'll explore how these massive systems of stars, gas, and dark matter developed and interacted over time. This part will reveal the dynamic processes that shape the diverse array of galaxies we see today. Dark matter, an enigmatic substance, plays a crucial role in the universe's structure. We'll delve into the evidence for dark matter, its influence on galaxy formation, and the ongoing quest to understand its nature. This section will shed light on one of the most intriguing aspects of modern cosmology. The universe's expansion is another key topic. We'll discuss Hubble's law, the discovery of the universe's accelerating expansion, and the concept of dark energy. These phenomena have profound implications for our understanding of the cosmos and its future trajectory. Next, we'll explore the large-scale structure of the universe, including the cosmic web and superclusters. We'll examine how these vast structures formed and what they reveal about the universe's overall architecture. This part will provide a macroscopic view of the cosmos. Black holes and quasars are among the most fascinating objects in the universe. We'll discuss their formation, characteristics, and the role they play in shaping their surroundings. This section will highlight the extreme environments and powerful phenomena associated with these cosmic entities. Cosmic phenomena and anomalies will be another focus. We'll cover gamma-ray bursts, gravitational waves, and other extraordinary events. These phenomena offer insights into the most energetic and mysterious processes in the universe. The future of the universe is a topic of much speculation and research. We'll explore different theories about its ultimate fate, including the Big Freeze, Big Crunch, and Big Rip. This part will consider the long-term evolution of the cosmos based on current scientific understanding. Our journey will also touch on the tools and technologies used to study the universe. From telescopes to space probes, these instruments have revolutionized our ability to observe and understand cosmic phenomena. We'll highlight some of the most significant advancements in this field. Throughout the video, we'll emphasize the ongoing quest to uncover the universe's secrets. Each discovery builds on previous knowledge, driving us closer to a comprehensive understanding of the cosmos. This narrative will underscore the dynamic and ever-evolving nature of cosmological research. The Big Bang theory stands as the leading explanation for how the universe began. This theory posits that the universe started from an incredibly hot and dense singularity, expanding rapidly in a fraction of a second. The evidence supporting this theory is compelling and multifaceted. One of the most significant pieces of evidence is the cosmic microwave background radiation. Discovered in 1965, this faint glow permeates the entire universe, offering a snapshot of the infant cosmos when it was just 380,000 years old. It serves as a residual heat signature from the Big Bang, providing crucial insights into the early universe. The expansion of the universe, first observed by Edwin Hubble in the 1920s, also supports the Big Bang theory. Hubble discovered that galaxies are moving away from us, with more distant galaxies receding faster. This observation suggests that the universe is expanding, implying it was once much smaller and denser. Nucleosynthesis, the process of forming new atomic nuclei, offers further evidence. The relative abundance of light elements like hydrogen, helium, and lithium in the universe aligns with predictions made by the Big Bang theory. These elements were formed in the first few minutes after the Big Bang, during a period known as Big Bang nucleosynthesis. Another piece of supporting evidence comes from the large-scale structure of the universe. The distribution of galaxies and cosmic structures follows patterns predicted by the Big Bang theory. Observations show a uniform and isotropic universe on large scales, consistent with the theory's expectations. Galactic redshift provides additional confirmation. As light from distant galaxies travels to us, it is stretched by the expanding universe, shifting towards the red end of the spectrum. This redshift is directly proportional to the distance of the galaxy, reinforcing the notion of an expanding universe from an initial singularity. Observations of galaxy clusters also support the Big Bang model. The distribution and movement of these clusters align with simulations based on the Big Bang theory. These clusters provide a large-scale confirmation of the universe's evolution from a hot, dense state to its current expansive form. The abundance of elements in the oldest stars aligns with the Big Bang theory. These stars, primarily composed of hydrogen and helium, reflect the composition of the early universe. Their elemental makeup supports the predictions of nucleosynthesis following the Big Bang. Cosmic inflation, a rapid expansion immediately after the Big Bang, is supported by the uniformity of the cosmic microwave background radiation. Inflation explains how the universe became so homogeneous and isotropic, smoothing out any initial irregularities and leading to the structure we observe today. The discovery of gravitational waves, ripples in space-time caused by massive cosmic events, also ties into the Big Bang theory. These waves provide a new way to probe the early universe, offering potential insights into conditions just after the Big Bang. The detection of these waves supports the dynamic processes predicted by the theory. High-energy particle physics experiments recreate conditions similar to those just after the Big Bang. These experiments, conducted in particle accelerators, help scientists understand the behavior of fundamental particles and forces in the universe's infancy. Results from these experiments consistently support the Big Bang model. Observations of distant galaxies and their evolution over time provide a direct look into the universe's past. By studying these galaxies, astronomers can trace the universe's expansion and development from the Big Bang to the present day. These observations offer a living record of the cosmos's history. Cosmological simulations, using advanced computer models, replicate the evolution of the universe from the Big Bang to now. These simulations, based on the laws of physics, produce structures and patterns consistent with astronomical observations. They offer a powerful tool for testing and refining the Big Bang theory. The isotropy of the universe, or its uniformity in all directions, supports the Big Bang model. Measurements show that the universe is remarkably consistent on large scales, with slight variations that can be explained by inflationary theory. This uniformity is a hallmark prediction of the Big Bang. Finally, the age of the universe, determined through various methods, aligns with the Big Bang timeline. Observations of the oldest stars, the rate of cosmic expansion, and the cosmic microwave background all point to a universe approximately 13.8 billion years old, matching the predictions of the Big Bang theory. At the very beginning, the universe existed in an extremely hot, dense state. Temperatures were so high that particles we are familiar with today couldn't exist in their current form. Instead, everything was a chaotic mix of energy and fundamental particles. During this initial phase, the universe was smaller than an atom. All the matter and energy of the universe were compressed into this infinitesimal point, creating a singularity with infinite density and temperature. This state set the stage for the rapid expansion that followed. Within the first second, the universe expanded and cooled enough for quarks and gluons to form. These fundamental particles are the building blocks of protons and neutrons. At these extreme temperatures, quarks existed freely in a hot, dense plasma. As the universe continued to expand, it cooled further, allowing quarks to combine into protons and neutrons. This process occurred within the first few minutes, setting the stage for the formation of atomic nuclei. This era is known as the quark epoch, a crucial period in the early universe. Protons and neutrons began to combine to form the first atomic nuclei. This process, called nucleosynthesis, produced the lightest elements, primarily hydrogen and helium. These elements would later become the fuel for star formation and cosmic evolution. The rapid expansion also affected the distribution of energy in the universe. Fluctuations in density and temperature created tiny variations that would eventually lead to the formation of galaxies and larger structures. These primordial fluctuations are imprinted in the cosmic microwave background radiation. During the first few minutes, the universe underwent significant changes in its fundamental forces. Initially unified, these forces began to separate as the universe cooled. Gravity, electromagnetism, and the strong and weak nuclear forces emerged as distinct interactions. The symmetry-breaking events in the early universe had profound implications for its structure. These events led to the creation of matter and antimatter nearly equal amounts. However, a slight imbalance allowed matter to dominate, giving rise to the universe we observe today. The concept of inflation plays a key role in understanding the initial conditions. A rapid exponential expansion occurred within a tiny fraction of a second, smoothing out irregularities and setting the stage for the large-scale structure of the universe. This theory helps explain the uniformity observed in the cosmic microwave background. Inflation also stretched tiny quantum fluctuations to macroscopic scales, planting the seeds for galaxy formation. These fluctuations grew over time, driven by gravitational attraction, eventually leading to the complex cosmic web of galaxies and clusters. As the universe cooled, it transitioned from a radiation-dominated era to a matter-dominated one. This shift allowed gravity to take over, influencing the formation of cosmic structures. Understanding this transition is crucial for tracing the universe's evolution from its hot, dense beginnings. The cooling universe allowed for the formation of stable atoms, marking the end of the plasma state. Electrons combined with protons and helium nuclei to form neutral atoms, making the universe transparent to radiation. This period is known as recombination and led to the decoupling of matter and radiation. The decoupling of matter and radiation resulted in the release of the cosmic microwave background radiation. This relic radiation provides a snapshot of the universe at the moment of recombination, offering a wealth of information about the early conditions and subsequent evolution. The initial conditions also set the abundance of different elements in the universe. The relative proportions of hydrogen, helium, and trace amounts of other light elements observed today match predictions from Big Bang nucleosynthesis, confirming our understanding of these early moments. Understanding the initial conditions of the universe helps us comprehend the vast cosmic history that followed. These moments laid the groundwork for everything that exists today, from the smallest particles to the largest galaxies, shaping the universe's intricate and awe-inspiring structure. During the inflation period, the universe experienced an extremely rapid expansion. This expansion happened in a fraction of a second, increasing the size of the universe exponentially. The idea of inflation was proposed to solve several problems in cosmology, such as the horizon and flatness problems. Inflation smoothed out any initial irregularities, making the universe homogeneous and isotropic on large scales. This uniformity is observed in the cosmic microwave background radiation, which shows a remarkably even distribution of temperature across the sky. The concept of inflation also explains the absence of magnetic monopoles. These hypothetical particles were predicted by early universe models, but have never been observed. Inflation would have diluted their presence, making them extremely rare in the observable universe. Quantum fluctuations during the inflation period were stretched to macroscopic scales. These tiny fluctuations in density and temperature became the seeds for all the structures we see in the universe today, such as galaxies, stars, and clusters. The energy driving inflation is thought to come from a hypothetical field called the inflaton field. As the universe expanded, the energy from this field decayed, transforming into particles and radiation, leading to the hot, dense state described by the Big Bang theory. Inflation theory predicts a flat universe. Observations of the cosmic microwave background and the distribution of galaxies support this prediction, showing that the geometry of the universe is very close to flat. This consistency further validates the inflationary model. The end of the inflation period, known as reheating, marks the transition to a universe filled with particles and radiation. During reheating, the energy from the inflaton field was transferred to standard particles, creating the hot, dense conditions of the early universe. Inflation theory also provides a mechanism for the formation of the large-scale structure of the universe. The initial quantum fluctuations, stretched during inflation, led to variations in density that eventually grew into galaxies and clusters under the influence of gravity. The rapid expansion during inflation moved regions of space that were once close together far apart. This explains why distant regions of the universe have similar properties, despite being beyond each other's causal influence since the Big Bang. The inflationary period is an essential component of modern cosmological models. It resolves several key issues left unexplained by the traditional Big Bang theory, providing a more comprehensive understanding of the universe's early evolution. Inflation's predictions are tested by observations of the cosmic microwave background. Detailed measurements of the CMB's temperature fluctuations and polarization offer critical insights into the conditions of the early universe and support the inflationary paradigm. Scientists are still working to understand the exact nature of the inflaton field. While its theoretical framework is robust, identifying the physical particle or field responsible for inflation remains an open question in cosmology. The success of the inflation theory in explaining the universe's large-scale structure has led to the development of various inflationary models. These models explore different scenarios for the inflaton field and its dynamics, enriching our understanding of the early universe. Inflation also has implications for the multiverse hypothesis. Some models suggest that inflation could occur repeatedly, creating multiple, potentially infinite universes with varying physical laws. This idea expands our perspective on the nature of reality itself. As our observational capabilities improve, we continue to test and refine the inflationary theory. Future discoveries, especially in the realm of gravitational waves, may provide new evidence or insights, further illuminating this critical period in the history of the universe. After the inflation period, the universe continued to expand and cool. During the first fractions of a second, it was still incredibly hot and dense. This environment was perfect for the formation of fundamental particles, the building blocks of matter. The earliest particles to form were quarks and leptons. Quarks are the constituents of protons and neutrons, while leptons include electrons and neutrinos. At these extreme temperatures, quarks and gluons existed in a free state, known as a quark-gluon plasma. As the universe expanded, it cooled enough for quarks to combine and form protons and neutrons. This process occurred within the first microseconds. Quarks were bound together by the strong nuclear force, mediated by gluons, to form these more stable particles. Neutrinos, which interact very weakly with matter, decoupled from the rest of the particles early on. They streamed freely through the universe, carrying away energy and information about the conditions of the early universe. These relic neutrinos still exist today, although they are very difficult to detect. Electrons, another type of lepton, also played a crucial role. As the universe cooled further, electrons combined with protons to form neutral hydrogen atoms. This process, known as recombination, occurred much later, but electrons were present from the very beginning. Photon interactions were dominant in the early universe. Photons, or particles of light, constantly interacted with other particles, maintaining thermal equilibrium. The universe was opaque during this time because photons were repeatedly scattered by free electrons and protons. As the universe continued to cool, the density of matter decreased. This allowed particles to interact less frequently, leading to the eventual decoupling of photons. This decoupling is what we observe today as the cosmic microwave background radiation. The formation of protons and neutrons set the stage for nucleosynthesis. During the first few minutes, these particles combine to form the nuclei of the lightest elements, such as hydrogen, helium, and small amounts of lithium and beryllium. This period is known as Big Bang nucleosynthesis. Quark confinement marked a significant transition. As the universe cooled, quarks became permanently confined within protons and neutrons, never existing freely again under normal conditions. This process is a fundamental aspect of quantum chromodynamics, the theory describing strong interactions. The formation of fundamental particles also involved the creation of antiparticles. For every particle, there exists a corresponding antiparticle with opposite charge. When particles and antiparticles meet, they annihilate each other, producing photons. This annihilation played a critical role in shaping the early universe. A slight asymmetry between matter and antimatter led to the dominance of matter in the universe. This imbalance, known as baryon asymmetry, ensured that some matter survived, after most particles and antiparticles annihilated each other. The exact cause of this asymmetry remains a topic of active research. The early universe's extreme conditions also allowed for the formation of exotic particles. These include hypothetical particles predicted by various theories beyond the standard model of particle physics. Understanding these particles could provide insights into the fundamental nature of the universe. High-energy particle collisions, similar to those in the early universe, are recreated in particle accelerators like the Large Hadron Collider. These experiments help scientists study the properties and interactions of fundamental particles, shedding light on conditions just after the Big Bang. The discovery of the Higgs boson in 2012 confirmed the existence of the Higgs field, which gives particles mass. This discovery was a significant milestone in understanding the formation and behavior of fundamental particles in the early universe. Research into the formation of fundamental particles continues to advance. As we develop more sophisticated technologies and theoretical models, our understanding of these processes deepens, revealing the intricate and fascinating history of the universe's earliest moments. In the first instant after the Big Bang, the universe was in a state of singularity. This marked the beginning of time and space as we understand it. The universe was incredibly hot, dense, and rapidly expanding. A tiny fraction of a second after the Big Bang, the inflation period occurred. During inflation, the universe expanded exponentially, smoothing out any initial irregularities. and setting the stage for the formation of large-scale structures. As the universe continued to expand, it cooled enough for quarks and gluons to form. These fundamental particles combined to create protons and neutrons. This process took place within the first microseconds of the universe's existence. About 1 second after the Big Bang, neutrinos decoupled from the rest of the matter, streaming freely through the universe. This decoupling allowed neutrinos to carry away energy and information about the early universe's conditions. Within the first 3 minutes, protons and neutrons began to combine through nuclear fusion, forming the nuclei of the lightest elements. This period of nucleosynthesis produced hydrogen, helium, and trace amounts of lithium and beryllium. After the first few minutes, the universe entered a period where it was dominated by radiation. Photons interacted constantly with electrons and protons, maintaining thermal equilibrium and keeping the universe opaque. Approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. This process, known as recombination, allowed photons to travel freely, leading to the release of the cosmic microwave background radiation. The cosmic microwave background radiation provides a snapshot of the universe at the time of recombination. This relic radiation has been stretched to longer wavelengths due to the universe's expansion, but it still carries vital information about the early universe's conditions. Following recombination, the universe entered the so-called dark ages. During this period, there were no stars or galaxies, and the universe was filled with neutral hydrogen. This era lasted for several 100 million years. The first stars began to form around 100 to 200 million years after the Big Bang. These population 3 stars were massive and short-lived, creating the first heavy elements through nuclear fusion and supernova explosions. The formation of the first stars brought an end to the Dark Ages, initiating the era of reionization. The ultraviolet light from these stars ionized the surrounding hydrogen gas, gradually making the universe transparent to ultraviolet light. As more stars and galaxies formed, they clustered together under the influence of gravity, creating the large-scale structures observed in the universe today. This process of hierarchical structure formation continued over billions of years. Around 1 billion years after the Big Bang, galaxies and clusters of galaxies became more prominent. The universe's large-scale structure began to resemble what we see today, with galaxies distributed in a cosmic web of filaments and voids. The expansion of the universe continued to accelerate, driven by a mysterious force known as dark energy. This acceleration has profound implications for the universe's future, influencing its ultimate fate. As the universe evolved, it went through various phases, each characterized by different dominant processes and components. From the formation of fundamental particles to the creation of stars and galaxies, each stage has contributed to the complex and dynamic cosmos we observe today. Primordial nucleosynthesis, also known as Big Bang nucleosynthesis, occurred within the first few minutes of the universe's existence. During this brief period, the universe was hot and dense enough for nuclear reactions to take place, forming the first atomic nuclei. The process began when the temperature dropped below about 1 billion degrees Kelvin. At this point, protons and neutrons, which had already formed from quarks, began to collide and stick together, forming the nuclei of the lightest elements. The first nuclei to form were deuterium, a heavy isotope of hydrogen, and helium-3. These nuclei were produced through a series of nuclear reactions involving protons and neutrons. The formation of deuterium was a critical step because it allowed for the creation of heavier nuclei. As deuterium nuclei formed, they quickly participated in further reactions, combining with protons and neutrons to create helium-4, the most stable and abundant product of primordial nucleosynthesis. Helium-4 nuclei, consisting of 2 protons and 2 neutrons, were able to form in significant quantities. In addition to helium-4, small amounts of other light nuclei, such as helium-3, deuterium, and lithium-7, were produced. However, the conditions of the early universe did not favor the formation of heavier elements, which would come much later in the interiors of stars. The relative abundances of these light elements provide a critical test for the Big Bang theory. Observations of the amounts of hydrogen, helium, and lithium in the oldest stars and in the interstellar medium match the predictions made by primordial nucleosynthesis models. The process of primordial nucleosynthesis lasted for only about 20 minutes. After this time, the universe had expanded and cooled to the point where nuclear reactions could no longer occur. The abundance of light elements was essentially frozen in place. The formation of these elements set the stage for the future chemical evolution of the universe. Hydrogen and helium, the primary products of primordial nucleosynthesis, became the raw material for the formation of stars and galaxies. The abundance of deuterium in particular provides important clues about the density of baryonic matter in the early universe. By comparing the observed abundance of deuterium with theoretical predictions, scientists can infer the amount of normal matter present at the time of nucleosynthesis. The process also depended on the neutron-to-proton ratio, which was determined by the weak nuclear force interactions in the first seconds after the Big Bang. This ratio influenced the relative amounts of hydrogen and helium produced during nucleosynthesis. Observations of the cosmic microwave background radiation also support the predictions of primordial nucleosynthesis. The slight variations in temperature observed in the CMB provide information about the conditions of the early universe, consistent with the abundances of light elements. Primordial nucleosynthesis is a key pillar of the Big Bang theory, linking the early universe's conditions with the chemical composition we observe today. It demonstrates how fundamental processes in the first minutes shaped the universe's subsequent development. The study of primordial nucleosynthesis continues to be an active area of research. Scientists use both observational data and theoretical models to refine our understanding of this critical period, providing insights into the universe's early history and fundamental physics. Future observations, especially those involving primordial elements in distant ancient stars and galaxies, may provide even more precise tests of nucleosynthesis theories. These observations could help resolve remaining questions and deepen our understanding of the universe's origins. Primordial nucleosynthesis is a remarkable example of how the universe's initial conditions and subsequent expansion governed the formation of the first elements. This process laid the groundwork for the complex chemistry and structure we observe in the cosmos today. Hydrogen and helium formation was a fundamental process during the early universe. These two elements, the simplest and lightest, were the primary products of primordial nucleosynthesis. Hydrogen, consisting of a single proton and electron, was the first element to form. As the universe cooled, protons and neutrons could combine to form deuterium, a heavy isotope of hydrogen with one proton and one neutron. Deuterium played a critical role in the formation of helium. Deuterium nuclei combined with protons to form helium-3, which then fused with other deuterium or helium-3 nuclei to produce helium-4, the most stable and abundant form of helium. Helium-4 nuclei, made up of 2 protons and 2 neutrons, were produced in significant quantities during the first few minutes after the Big Bang. This process was efficient because helium-4 is very stable, making it the predominant helium isotope in the universe. The conditions of the early universe favored the formation of these light elements. The temperature and density were just right for nuclear reactions to occur, allowing protons and neutrons to combine and form stable nuclei. The relative abundance of hydrogen and helium in the universe today reflects the conditions during primordial nucleosynthesis. About 75% of the baryonic mass of the universe is hydrogen, while roughly 25% is helium-4, with trace amounts of other light elements. This ratio of hydrogen to helium is a key piece of evidence supporting the Big Bang theory. Observations of the oldest stars and distant galaxies show the same proportions, confirming the predictions made by models of the early universe. The formation of hydrogen and helium had profound implications for the future evolution of the universe. These elements became the building blocks for the first stars and galaxies, providing the raw material for subsequent generations of stars and the synthesis of heavier elements. In the cores of the first stars, hydrogen fused into helium through nuclear fusion, releasing energy and driving the star's luminosity. This process continues in stars today, powering the light and heat we observe from our own sun and countless other stars. Helium formation during the Big Bang also influenced the development of the cosmic microwave background radiation. The abundance of helium affects the density and temperature of the early universe, leaving an imprint on the CMB that we can observe today. The study of hydrogen and helium formation helps scientists understand the universe's early conditions. By measuring the abundances of these elements in various cosmic environments, researchers can test and refine their models of primordial nucleosynthesis. Observations of deuterium, a key intermediate in helium production, provide additional insights into the density of baryonic matter in the early universe. The abundance of deuterium observed in ancient gas clouds and stars matches predictions, supporting the Big Bang model. The formation of hydrogen and helium also set the stage for the chemical complexity of the universe. These elements combined with other nuclei through stellar processes to create the heavier elements necessary for planets, life, and the diverse structures we see in the cosmos. Research into the formation of hydrogen and helium continues to advance our understanding of the early universe. New observational techniques and theoretical models help scientists probe deeper into this critical period, revealing more about the origins of the universe's elemental composition. Understanding the formation of hydrogen and helium provides a foundation for studying the subsequent stages of cosmic evolution. These elements are the starting point for the rich tapestry of chemical and physical processes that have shaped the universe over billions of years. Neutrons and protons played a crucial role in the early universe's evolution. These particles, known as nucleons, are the building blocks of atomic nuclei. Their interactions determined the formation of the first elements. In the moments after the Big Bang, the universe was hot enough for quarks and gluons to exist freely. As it expanded and cooled, quarks combined to form protons and neutrons. This process, called hadronization, occurred within microseconds. Protons, consisting of 2 up quarks and 1 down quark, are positively charged. Neutrons, made up of 2 down quarks and 1 up quark, carry no charge. Despite this difference, both particles are held together by the strong nuclear force. The balance between protons and neutrons was critical for nucleosynthesis. Initially, there were slightly more protons than neutrons due to the slightly higher mass of the neutron. This imbalance influenced the types and amounts of elements that could form. Neutrons are unstable when free, decaying into protons, electrons, and antineutrinos, with a half-life of about 10 minutes. In the early universe, some neutrons decayed before they could combine with protons, further reducing their number relative to protons. Protons and neutrons combined to form deuterium, a heavy isotope of hydrogen. Deuterium nuclei, composed of 1 proton and 1 neutron, were the first step in the formation of heavier elements. This process required precise conditions of temperature and density. Once deuterium formed, it quickly participated in further nuclear reactions. 2 deuterium nuclei could fuse to create helium-3, which then fused with another deuterium, or helium-3 nucleus, to form helium-4. These reactions were essential for building up the light elements. The relative abundance of neutrons and protons determined the yield of different elements. A higher neutron-to-proton ratio would have resulted in more helium and other heavier elements, while a lower ratio would have favored the formation of hydrogen. Protons remained as the dominant component of hydrogen, the most abundant element in the universe. Hydrogen atoms, consisting of a single proton and an electron, became the primary building blocks for the formation of stars and galaxies. Neutrons, despite being less abundant, were crucial for the formation of helium and other light elements. Their presence allowed for the creation of stable nuclei with multiple protons, overcoming the electrostatic repulsion between positively charged protons. The interactions between protons and neutrons were governed by the strong nuclear force. This fundamental force binds quarks together within nucleons and nucleons together within atomic nuclei. It is one of the 4 fundamental forces of nature. Understanding the role of neutrons and protons in the early universe helps scientists model the conditions of primordial nucleosynthesis. Observations of elemental abundances provide critical tests for these models, confirming or refining our theories about the universe's beginnings. The behavior of neutrons and protons also has implications for modern physics. Studies of their interactions contribute to our understanding of nuclear forces, particle physics, and the fundamental structure of matter. Research into neutron and proton behavior continues to be a dynamic field. Advanced experiments and observations, from particle accelerators to astronomical surveys, deepen our knowledge of these particles' roles in both the early universe and contemporary physics. The story of neutrons and protons is a testament to the intricate processes that shaped the cosmos. Their interactions laid the groundwork for the chemical complexity and structural diversity of the universe, influencing everything from the formation of stars to the elements that make up our own planet. Light element abundance in the universe provides critical evidence for the Big Bang theory. These elements, primarily hydrogen, helium, and small amounts of lithium, were formed during the first few minutes after the Big Bang. Hydrogen is the most abundant element in the universe, making up about 75% of the baryonic mass. Its abundance is a direct result of the initial conditions of the early universe and the processes of primordial nucleosynthesis. Helium, the second most abundant element, accounts for about 25% of the baryonic mass. The formation of helium-4 was a key outcome of the nuclear reactions that occurred in the early universe, a process well predicted by the Big Bang model. The abundance of deuterium, an isotope of hydrogen, serves as a sensitive probe of the conditions during nucleosynthesis. Because deuterium is easily destroyed in stellar interiors, its observed abundance provides a snapshot of the early universe's density and temperature. Lithium, although much less abundant than hydrogen and helium, also formed during primordial nucleosynthesis. The observed amount of lithium-7, however, presents some discrepancies with theoretical predictions, a problem known as the cosmological lithium problem. The study of light element abundances involves precise measurements of these elements in various cosmic environments. Astronomers use spectroscopy to determine the chemical composition of stars, gas clouds, and distant galaxies, comparing these observations with theoretical models. The observed abundances of these light elements align closely with the predictions of the Big Bang nucleosynthesis theory. This agreement provides strong support for the model, confirming our understanding of the universe's early moments. Differences in the abundance of light elements can also provide insights into the history and evolution of galaxies. For instance, regions with varying amounts of deuterium can indicate different star formation histories and processes. The precise measurement of helium abundance, particularly helium-3 and helium-4, helps constrain models of stellar evolution and the interstellar medium. These measurements are crucial for understanding how stars and galaxies process and redistribute elements. High redshift observations allow scientists to study the light element abundances in the early universe. By examining ancient gas clouds and distant quasars, researchers gain insights into the primordial conditions that shaped the cosmos. The abundance of deuterium in particular serves as a critical test for cosmological models. Because deuterium is only produced during the Big Bang and destroyed in stars, its observed abundance can help determine the density of baryonic matter in the universe. The cosmological lithium problem highlights the challenges and complexities of understanding nucleosynthesis. The discrepancy between observed and predicted lithium-7 abundances suggests there may be gaps in our understanding of nuclear reactions or stellar processes. Research into the abundances of light elements continues to refine our knowledge of the early universe. New observational techniques and theoretical developments aim to resolve outstanding issues and improve the accuracy of our cosmological models. Understanding light element abundance also has implications for other areas of astrophysics. It informs studies of star formation, galactic evolution, and the chemical enrichment of the universe, linking the earliest moments of the cosmos to its current state. The patterns and distributions of light elements tell a story of the universe's first few minutes, providing a window into the conditions and processes that defined the primordial era. These abundances serve as a lasting imprint of the Big Bang, offering a glimpse into the universe's origins. The transition to a transparent universe marks a pivotal moment in cosmic history. This era, known as recombination, occurred around 380,000 years after the Big Bang. During recombination, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. This process drastically reduced the number of free electrons and allowed photons to travel freely for the first time. As the universe became transparent, it released the cosmic microwave background radiation. This relic radiation provides a snapshot of the universe at the moment of recombination, carrying vital information about its early conditions. Before recombination, the universe was a hot, dense plasma where photons constantly interacted with free electrons and protons. This scattering kept the universe opaque, preventing light from traveling long distances. The cooling of the universe allowed electrons to bind to protons, reducing the scattering of photons. This decoupling of matter and radiation meant that photons could now move unimpeded, making the universe transparent. The cosmic microwave background radiation we observe today is the redshifted remnant of the light released during recombination. It has been stretched to microwave wavelengths by the universe's expansion over billions of years. Recombination also marked the end of the radiation-dominated era and the beginning of the matter-dominated era. The formation of neutral atoms allowed gravity to take over, leading to the growth of structures like galaxies and clusters. The transition to a transparent universe set the stage for the formation of the first stars and galaxies. With photons able to travel freely, the temperature fluctuations imprinted on the cosmic microwave background provided the seeds for cosmic structure formation. The cosmic microwave background radiation is remarkably uniform, but it contains slight anisotropies. These tiny temperature fluctuations reflect the density variations in the early universe, which eventually led to the large-scale structure we observe today. Detailed measurements of the cosmic microwave background have been made by missions like COBE, WMAP, and Planck. These observations have provided critical insights into the universe's age, composition, and rate of expansion. The information encoded in the cosmic microwave background allows scientists to test and refine cosmological models. It offers a wealth of data about the early universe, including the density of different components like dark matter and dark energy. The transition to a transparent universe also has implications for the subsequent epochs of cosmic history. It marks the point at which light could travel across the universe, enabling the formation of complex structures and the development of the observable cosmos. Recombination is a well-understood process, but ongoing research continues to uncover new details about this critical period. Advances in observational technology and theoretical modeling help to deepen our understanding of how the universe became transparent. The study of this transition helps scientists trace the universe's evolution from its hot, dense beginnings to its current state. By understanding recombination, researchers gain insights into the processes that shape the universe's large-scale structure. The transparency of the universe remains a key area of investigation in cosmology. By probing this era, scientists hope to uncover more about the fundamental forces and particles that governed the early universe, providing a clearer picture of its origins and development. The recombination era was a significant epoch in the history of the universe. It began roughly 380,000 years after the Big Bang, marking the time when electrons and protons combined to form neutral hydrogen atoms. As the universe cooled, the energy levels dropped, allowing electrons to bind with protons. This process reduced the number of free charge particles, decreasing the scattering of photons and leading to a transparent universe. Before recombination, the universe was a hot, dense plasma where light could not travel far without being scattered by free electrons. This constant interaction kept the universe opaque. With the formation of neutral hydrogen, photons were no longer scattered as frequently. This allowed light to travel freely, resulting in the release of the cosmic microwave background radiation, which we observe today. The cosmic microwave background radiation provides a snapshot of the universe at the moment of recombination. It carries imprints of the density fluctuations that existed at that time, offering crucial insights into the early universe's conditions. Recombination marked the transition from a radiation-dominated universe to a matter-dominated one. The reduction in free electrons meant that photons could decouple from matter, making the universe transparent for the first time. This era set the stage for the subsequent formation of cosmic structures. The density fluctuations imprinted on the cosmic microwave background served as the seeds for the formation of galaxies, stars, and clusters. The slight temperature variations in the cosmic microwave background reflect the density differences in the early universe. These anisotropies are key to understanding how matter eventually coalesced into the large-scale structures we see today. Measurements of the cosmic microwave background by missions like COBE, WMAP, and Planck have provided detailed maps of these temperature fluctuations. These observations have helped refine our understanding of the universe's age, composition, and rate of expansion. The recombination era also influenced the chemical makeup of the universe. The formation of neutral hydrogen and helium atoms during this time determined the initial chemical composition that would be later enriched by stellar processes. Understanding recombination is crucial for cosmology. It provides a clear boundary between the opaque early universe and the transparent universe we observe now, allowing scientists to study the initial conditions that led to cosmic evolution. Research into the recombination era continues to evolve. Advances in observational techniques and theoretical models help to uncover more details about this critical period, deepening our understanding of how the universe transitioned to transparency. The study of recombination also has implications for understanding the nature of dark matter and dark energy. The patterns observed in the cosmic microwave background offer clues about these mysterious components of the universe. As scientists continue to explore the recombination era, they gain a better grasp of the processes that governed the early universe. This knowledge helps piece together the cosmic timeline from the Big Bang to the formation of the first galaxies and beyond. The recombination era represents a turning point in cosmic history. By examining this period, researchers unlock the secrets of the universe's infancy, shedding light on the fundamental forces and particles that shaped the cosmos into its current form. The emergence of the cosmic microwave background was a monumental event in the history of the universe. This relic radiation offers a glimpse into the universe when it was just 380,000 years old. As the universe transitioned from the opaque state of the recombination era, photons were able to travel freely for the first time. This decoupling of matter and radiation allowed the cosmic microwave background to emerge. The cosmic microwave background is the afterglow of the Big Bang. It fills the entire universe, providing a snapshot of the early cosmos at the moment of recombination. This radiation is remarkably uniform in all directions, but it contains tiny fluctuations in temperature. These fluctuations reflect the density variations that existed in the early universe. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang theory. It confirmed the predictions that such a background radiation would exist. Detailed measurements of the cosmic microwave background have been made by various missions, including COBE, WMAP, and Planck. These observations have mapped the minute temperature variations with great precision. The cosmic microwave background has a temperature of about 2.7 Kelvin, just above absolute zero. This cold temperature is due to the redshift of the radiation, as the universe expanded over billions of years. The tiny fluctuations in the cosmic microwave background are essential for understanding the large-scale structure of the universe. They indicate regions of slightly different densities that would eventually grow into galaxies and clusters under the influence of gravity. The cosmic microwave background also provides information about the universe's composition. By analyzing its fluctuations, scientists can determine the relative amounts of dark matter, dark energy, and normal matter. The polarization of the cosmic microwave background gives additional clues about the early universe. This polarization pattern is influenced by the density fluctuations and the gravitational waves from the inflationary period. One of the remarkable features of the cosmic microwave background is its isotropy. The uniformity of this radiation in all directions supports the idea that the universe underwent a rapid expansion, or inflation, shortly after the Big Bang. The cosmic microwave background serves as a cosmic backdrop against which the evolution of the universe can be studied. It provides a reference point for measuring the expansion rate and understanding the universe's overall geometry. Research into the cosmic microwave background continues to refine our understanding of the early universe. Each new observation adds to the detailed picture of the cosmos's infancy and its subsequent evolution. The cosmic microwave background also offers insights into fundamental physics. It provides a unique laboratory for testing theories about the early universe, particle physics, and the nature of dark matter and dark energy. The emergence of the cosmic microwave background marked the end of the universe's initial opaque phase and the beginning of an era where light could travel freely. This transition set the stage for the formation of the first stars and galaxies, shaping the universe as we know it today. The properties of the cosmic microwave background, or CMB, are fundamental to our understanding of the universe. One of its most important properties is its uniform temperature, approximately 2.7 Kelvin, which is incredibly close to absolute zero. Despite this uniformity, the CMB has tiny temperature fluctuations on the order of 1 part in 100,000. These minute variations are crucial as they reflect the density fluctuations in the early universe that eventually led to the formation of galaxies and large-scale structures. The CMB is a blackbody radiation, meaning it has a characteristic spectrum that depends only on its temperature. This spectrum peaks at microwave wavelengths, corresponding to the peak emission of a blackbody at 2.7 Kelvin. One significant property of the CMB is its isotropy. It is nearly the same in every direction, suggesting that the early universe was homogeneous and isotropic on large scales. This observation supports the theory of cosmic inflation. The tiny anisotropies, or temperature fluctuations in the CMB, are caused by sound waves propagating through the hot, dense plasma of the early universe. These acoustic oscillations left imprints on the CMB that we observe today. The polarization of the CMB provides additional information. This polarization results from the scattering of photons off electrons during the recombination era, and carries imprints of both density fluctuations and gravitational waves from the early universe. The CMB's power spectrum, a plot of temperature fluctuation amplitude versus angular scale, shows a series of peaks and troughs. These features correspond to the sound waves in the early universe and provide information about the universe's composition and geometry. From the CMB, we learn about the baryon density, dark matter density, and dark energy density. The relative heights and positions of the peaks in the power spectrum help determine these fundamental cosmological parameters. The CMB also allows us to measure the Hubble constant, the rate of the universe's expansion. By comparing the observed CMB fluctuations with theoretical models, scientists can infer the current expansion rate of the universe. Observations of the CMB have revealed the age of the universe. Detailed measurements indicate that the universe is about 13.8 billion years old, based on the time it took for the observed structures to evolve from the initial fluctuations. The CMB's properties also provide evidence for the curvature of the universe. Observations show that the universe is very close to flat, meaning that parallel lines remain parallel over cosmological distances, consistent with predictions from inflationary theory. The integrated Sachs-Wolf effect, a phenomenon observed in the CMB, provides evidence for dark energy. This effect occurs when photons from the CMB pass through potential wells in the universe's structure, gaining energy and indicating an accelerating universe. The Sunyaev-Zeldovich effect, another property observed in the CMB, involves the scattering of CMB photons off hot electrons in galaxy clusters. This effect helps measure the properties of galaxy clusters and the distribution of matter in the universe. The CMB's uniformity and the slight fluctuations also provide constraints on the types of particles that existed in the early universe. The observed properties are consistent with the standard model of particle physics, though they also leave room for new physics. Overall, the properties of the CMB are a treasure trove of information about the early universe, its composition, its expansion, and its large-scale structure. The CMB continues to be a critical tool for cosmologists, helping to unravel the mysteries of the cosmos and refine our understanding of fundamental physics. Discoveries and measurements of the cosmic microwave background have revolutionized our understanding of the universe. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson provided direct evidence of the Big Bang, earning them the Nobel Prize in Physics. The COBE satellite, launched in 1989, made the first precise measurements of the CMB's temperature fluctuations. COBE's findings confirmed the blackbody nature of the CMB and detected the tiny anisotropies, laying the groundwork for future studies. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided much higher resolution maps of the CMB. WMAP's data allowed scientists to refine the age of the universe, determine the composition of dark matter and dark energy, and measure the Hubble constant with greater accuracy. The Planck satellite, launched in 2009, further enhanced our understanding with even higher resolution and sensitivity. Planck's observations detailed the temperature fluctuations and polarization of the CMB, providing a wealth of information about the early universe. Planck's data confirmed that the universe is approximately 13.8 billion years old. It also revealed more about the universe's geometry, indicating that it is very close to flat, consistent with predictions from the inflationary model. Planck and WMAP both measured the CMB's power spectrum, showing a series of acoustic peaks. These peaks correspond to the sound waves in the early universe's plasma and provide insights into the universe's density, composition, and expansion rate. Measurements of the CMB have provided evidence for the existence of dark matter and dark energy. By analyzing the CMB's fluctuations, scientists can infer the amounts of these mysterious components that dominate the universe's mass-energy content. The polarization measurements from Planck and other experiments have helped detect the signature of primordial gravitational waves. These waves, generated during inflation, leave a distinctive pattern in the CMB's polarization, offering clues about the early universe's dynamics. High-resolution observations of the CMB have also revealed details about the large-scale structure of the universe. The patterns of temperature fluctuations correspond to the seeds of galaxies and clusters, allowing scientists to trace the growth of cosmic structures over time. The integrated Sachs-Wolf effect observed in the CMB provides additional evidence for dark energy. This effect occurs when CMB photons gain energy while passing through evolving gravitational potential wells, indicating an accelerating universe. The Sunyaev-Zeldovich effect, detected in the CMB, measures the interaction of CMB photons with hot gas in galaxy clusters. This effect helps study the properties of clusters and the distribution of matter in the universe. Ground-based and balloon-borne experiments, such as the Atacama Cosmology Telescope and the South Pole Telescope, complement satellite observations. These experiments provide high-resolution maps of the CMB and probe its small-scale features. The BICEP and Keck array experiments focus on detecting the polarization of the CMB. Their results contribute to understanding primordial gravitational waves and testing theories of cosmic inflation. Future missions and experiments aim to further refine our measurements of the CMB. Projects like the Simons Observatory and the CMB S4 experiment will provide even more detailed maps, enhancing our understanding of the universe's earliest moments. Discoveries and measurements of the CMB continue to shape our knowledge of cosmology. Each new observation provides deeper insights into the universe's origin, composition, and evolution, confirming the Big Bang model and revealing the fundamental processes that have shaped the cosmos. The end of the Dark Ages was a transformative period in the universe's history. After the era of recombination, the universe was filled with neutral hydrogen and helium, remaining dark and devoid of stars for hundreds of millions of years. During this time, slight density fluctuations from the cosmic microwave background began to grow under the influence of gravity. These fluctuations eventually led to the formation of the first structures in the universe. As these regions of higher density collapsed, they formed the first stars, known as population 3 stars. These stars were massive, hot, and short-lived, composed almost entirely of hydrogen and helium. The formation of the first stars marked the end of the Dark Ages. These population 3 stars emitted intense ultraviolet light, which began to ionize the surrounding hydrogen gas, creating bubbles of ionized gas in the intergalactic medium. This process of reionization was a key event in cosmic history. It gradually transformed the universe from being opaque to ultraviolet light to being transparent, allowing light to travel freely through space once again. Reionization was not instantaneous, but occurred over hundreds of millions of years. The first stars and galaxies played a crucial role in this process, as their intense radiation continued to ionize the surrounding gas. The formation of the first galaxies followed the birth of the first stars. These early galaxies were small and faint, merging over time to form larger, more complex structures. Quasars, the extremely luminous centers of young galaxies powered by supermassive black holes, also contributed to reionization. Their intense energy output further ionized the intergalactic medium. Observations of distant quasars and galaxies have provided evidence for the timeline of reionization. The light from these objects is absorbed by neutral hydrogen, creating a signature in their spectra that indicates the presence of ionized bubbles. The study of the 21-centimeter line, a specific wavelength of light emitted by neutral hydrogen, offers a tool for probing the end of the Dark Ages. This line allows astronomers to map the distribution of hydrogen in the early universe and trace the progress of reionization. The end of the Dark Ages and the era of reionization had profound effects on the universe's evolution. It set the stage for the formation of larger cosmic structures and influenced the distribution and properties of galaxies. Understanding this period helps scientists piece together the timeline of the universe's history. By studying the end of the Dark Ages, researchers gain insights into the processes that led to the rich and diverse cosmos we observe today. Current and future telescopes, like the James Webb Space Telescope, aim to observe the earliest galaxies and stars directly. These observations will provide a clearer picture of how the first light sources emerged and how reionization progressed. The end of the Dark Ages represents a pivotal transition from a dark, featureless universe to one filled with light and structure. It marks the dawn of the cosmic dawn, where the first galaxies illuminated the universe and began shaping its future. Research into this epoch continues to reveal the intricate processes that transformed the early universe. Each discovery brings us closer to understanding the origins of stars, galaxies, and the large-scale structure that defines our universe today. The cooling of the universe was a gradual process that began after the initial explosive expansion of the Big Bang. As the universe expanded, the density and temperature of the radiation and matter within it decreased. In the first few seconds, the universe was extremely hot and dense. Temperatures were so high that particles like protons and neutrons could not yet form stable nuclei. Instead, the universe was a hot plasma of quarks, gluons, and other elementary particles. Within the first few minutes, the temperature dropped enough to allow protons and neutrons to combine, forming the first atomic nuclei. This period, known as nucleosynthesis, led to the creation of light elements like hydrogen, helium, and trace amounts of lithium. As the universe continued to expand, it cooled further. Around 380,000 years after the Big Bang, the temperature had dropped sufficiently for electrons to combine with protons, forming neutral hydrogen atoms. This process, known as recombination, made the universe transparent to light for the first time. The formation of neutral hydrogen allowed photons to travel freely, leading to the release of the cosmic microwave background radiation. This radiation provides a snapshot of the universe at the moment of recombination, showing a much cooler universe than before. The cooling continued over millions of years. As the universe expanded, the average temperature of the gas decreased. This cooling allowed the first gravitational instabilities to grow, leading to the formation of the first stars and galaxies. In these cooler conditions, regions of slightly higher density began to collapse under their own gravity. The first stars, known as population 3 stars, formed from these collapsing gas clouds. Their intense radiation contributed to further cooling and the reionization of the universe. The cooling of the universe also allowed for the formation of molecular hydrogen. These molecules were crucial for the cooling of gas clouds, enabling them to collapse more efficiently and form stars and galaxies. As stars and galaxies formed, they began to heat their surroundings through radiation and supernova explosions. However, on larger scales, the universe continued to cool as it expanded. The interplay between heating from stars and cooling from expansion shaped the universe's evolution. The cooling universe had implications for the formation of cosmic structures. Lower temperatures allowed for the gradual buildup of galaxies and clusters of galaxies. Over billions of years, these structures grew and evolved into the complex cosmic web we observe today. Cooling also affected the types of stars that formed. Initially, massive stars dominated, but as the universe cooled further, lower mass stars became more common. These stars had longer lifetimes and contributed to the enrichment of the interstellar medium with heavier elements. The cooling of the universe can be traced through observations of the cosmic microwave background and the large-scale structure of the cosmos. By studying these remnants, scientists can reconstruct the thermal history of the universe. Understanding the cooling of the universe helps explain the conditions that led to the formation of galaxies, stars, and planets. It provides a framework for understanding the processes that shape the universe's evolution. Future observations and theoretical developments will continue to refine our understanding of the universe's cooling. By probing deeper into the cosmic past, scientists aim to uncover more details about the transition from a hot, dense plasma to the cool, structured universe we see today. The cooling of the universe is a fundamental aspect of its history. It set the stage for the formation of all cosmic structures, influencing the development of galaxies, stars, and eventually, the conditions necessary for life to emerge. Population 3 stars were the first generation of stars to form in the universe. These stars were composed almost entirely of hydrogen and helium, with virtually no heavier elements. The formation of population 3 stars began in the dense gas clouds that emerged from the initial density fluctuations in the early universe. As these clouds collapsed under gravity, they heated up, eventually reaching the temperatures necessary for nuclear fusion. Population 3 stars were much more massive than most stars we see today. Some of them had masses hundreds of times that of the Sun. Their large masses led to very high core temperatures and short lifespans, often only a few million years. Because they were so massive, population 3 stars burned their fuel quickly and were incredibly luminous. They emitted large amounts of ultraviolet radiation, which played a crucial role in ionizing the universe, making it transparent to ultraviolet light. The intense radiation from population 3 stars ionized the surrounding hydrogen gas, creating bubbles of ionized gas that expanded over time. This reionization process was essential for the transition from the Dark Ages to a universe filled with light. The life cycle of population 3 stars ended in spectacular supernova explosions. These explosions were powerful enough to create and disperse heavier elements like carbon, oxygen, and iron into the surrounding interstellar medium. The supernovae of population 3 stars enriched the primordial gas with these new elements, setting the stage for the formation of subsequent generations of stars and the chemical complexity necessary for planets and life. Population 3. Stars are believed to have played a critical role in the early universe's evolution. Their intense radiation and supernova explosions helped shape the first galaxies and influenced the formation of later stellar populations. Despite their importance, population 3 stars have not yet been directly observed. Their existence is inferred from the chemical composition of ancient stars and gas clouds, as well as from theoretical models of star formation. Modern telescopes and upcoming observatories like the James Webb Space Telescope aim to detect the faint signatures of these ancient stars. Finding population 3 stars would provide direct evidence of the universe's first light sources. Understanding population 3 stars helps scientists piece together the timeline of cosmic evolution. These stars were the first to forge heavier elements, laying the groundwork for the rich chemical diversity observed in the universe today. The study of population 3 stars also provides insights into the processes of star formation and evolution. By understanding these early stars, researchers can better grasp how subsequent generations of stars and galaxies formed and evolved. Simulations of the early universe show how population 3 stars formed in dense regions of gas and how their supernova explosions influenced the surrounding environment. These models help explain the distribution and abundance of elements in the universe. The impact of population 3 stars extends beyond their immediate surroundings. Their radiation and supernova helped drive the formation of larger cosmic structures, influencing the development of galaxies and clusters. The legacy of population 3 stars is still evident today in the chemical composition of the oldest stars and the interstellar medium. By studying these relics, scientists continue to learn more about the first stars and the role they played in shaping the universe. The first light in the universe marked a transformative period. This epoch began with the formation of the first stars, known as population 3 stars. These stars were the first to shine, piercing the darkness of the cosmic night. As the first stars ignited, their intense ultraviolet radiation began to ionize the surrounding hydrogen gas. This process created regions of ionized gas, leading to the gradual reionization of the universe. These early sources of light were crucial in ending the cosmic dark ages. The light from these first stars played a key role in shaping the universe. It heated the surrounding gas, preventing it from collapsing too quickly and influencing the formation of subsequent generations of stars and galaxies. This feedback mechanism regulated star formation in the early universe. The radiation from the first stars also contributed to the reionization process. As these stars burned brightly, they emitted enough energy to ionize the intergalactic medium, transforming it from neutral hydrogen to ionized plasma. This reionization allowed light to travel freely across the universe. The light from these early stars was incredibly powerful, Population 3 stars, being much more massive and luminous than most stars we see today, emitted copious amounts of ultraviolet and even X-ray radiation. This intense light played a significant role in the early universe's thermal and chemical evolution. Supernova explosions of the first stars further enriched the universe with heavy elements. These explosions scattered elements like carbon, oxygen, and iron into space, seeding the formation of new stars and planets. This enrichment was critical for the development of more complex structures. The light from the first stars also provided the energy necessary to drive chemical reactions in the surrounding gas. These reactions led to the formation of molecules that could cool gas clouds, facilitating the formation of new stars and galaxies. The era of the first light is a subject of intense study. Astronomers use both observations and simulations to understand how the first stars formed, how they influenced their environment, and how they contributed to the ionization of the universe. Future telescopes, like the James Webb Space Telescope, aim to observe the first galaxies and stars directly. These observations will provide invaluable insights into the properties of the first light sources and their impact on the early universe. The first light in the universe set the stage for the formation of galaxies. As the first stars clustered together under the influence of gravity, they formed the earliest galaxies. These nascent galaxies grew through mergers and the accretion of gas, evolving into the complex structures we see today. The transition from the Dark Ages to a universe filled with light was a gradual process. It involved the interplay between the formation of the first stars, their radiation, and the ionization of the intergalactic medium. This period laid the foundation for all subsequent cosmic evolution. The study of the first light also helps scientists understand the conditions of the early universe. By examining the light from ancient stars and galaxies, researchers can infer the physical conditions and processes that were prevalent at that time. The light from the first stars continues to travel across the universe. By observing distant objects, astronomers can look back in time and study the properties of the universe when it was just a fraction of its current age. This window into the past provides critical information about the universe's early stages. The legacy of the first light is still present today. The chemical elements produced by the first stars are found in ancient stars and interstellar gas, offering clues about the processes that took place during the universe's formative years. This enduring legacy shapes our understanding of cosmic history. The emergence of the first light in the universe was a pivotal moment that transformed the cosmos. It marked the beginning of the era of galaxies, stars, and complex structures, setting the stage for the rich and diverse universe we observe today. The first stars played a crucial role in the formation of further elements. These stars, known as population 3 stars, were massive and burned through their nuclear fuel rapidly. In their cores, nuclear fusion processes created heavier elements from the primordial hydrogen and helium. As these stars exhausted their nuclear fuel, they ended their lives in cataclysmic supernova explosions. These explosions were powerful enough to create and disperse a variety of heavier elements, including carbon, oxygen, and iron, into the surrounding space. The elements produced in these supernovae mixed with the primordial gas, enriching the interstellar medium with the building blocks necessary for the formation of new stars and planets. This process of enrichment set the stage for the next generation of stars, known as population 2 stars. Population 2 stars formed from gas clouds that had been enriched by the first supernovae. These stars contained higher amounts of heavy elements compared to population 3 stars, allowing for more complex nuclear fusion processes and the formation of a broader range of elements. The cycle of star formation and supernova explosions continued, each generation of stars contributing more heavy elements to the interstellar medium. This ongoing process of nucleosynthesis gradually increased the metallicity, or the abundance of elements heavier than helium, in the universe. The elements produced by successive generations of stars eventually led to the formation of population 1 stars, like our Sun. These stars formed in regions of space that had been thoroughly enriched by previous supernovae, allowing them to form with a higher metallicity. In addition to producing heavy elements, the first stars also played a role in the formation of complex molecules. The radiation from these stars drove chemical reactions in the surrounding gas, leading to the formation of molecules like molecular hydrogen, which played a key role in cooling gas clouds and facilitating further star formation. The presence of heavier elements and molecules in the interstellar medium influenced the physical properties of gas clouds, affecting their ability to collapse and form new stars. This feedback mechanism helped regulate the rate of star formation in the early universe. The formation of heavy elements also had implications for the development of planetary systems. Elements like carbon, oxygen, silicon, and iron are essential for the formation of rocky planets and the complex chemistry necessary for life. The first stars set the stage for the eventual emergence of habitable worlds. Supernova explosions from the first stars also played a role in triggering further star formation. The shock waves from these explosions compressed nearby gas clouds, initiating the collapse of these clouds and the formation of new stars. This process contributed to the growth of stellar populations and the evolution of galaxies. The role of the first stars in element formation is a key area of study in astrophysics. By understanding how these stars produced and dispersed heavy elements, scientists can gain insights into the chemical evolution of the universe and the origins of the elements that make up planets and life. Observations of ancient stars and gas clouds provide evidence of the enrichment processes that occurred in the early universe. By studying the chemical compositions of these objects, astronomers can trace the history of nucleosynthesis and the contributions of the first stars. Theoretical models and simulations help scientists understand the complex interactions between star formation, supernova explosions, and the enrichment of the interstellar medium. These models provide valuable insights into the processes that shape the chemical evolution of the universe. Future observations, particularly with advanced telescopes, will continue to refine our understanding of the role of the first stars in element formation. By observing the earliest galaxies and stars, astronomers hope to directly detect the signatures of the first nucleosynthesis processes. The role of the first stars in further element formation is a fundamental aspect of cosmic evolution. Their contributions to the chemical enrichment of the universe laid the foundation for the complex structures and diverse elements that make up the cosmos today. The formation of early galaxies began in the universe's first billion years. Small fluctuations in the density of matter, left over from the Big Bang, grew under the influence of gravity, pulling gas and dark matter together to form the first galactic structures. These early galaxies were much smaller and less organized than the galaxies we see today. They were irregular in shape and consisted mostly of gas with few stars. As more matter accumulated, these galaxies began to grow and evolve. The first stars in these early galaxies were massive and short-lived. Their intense radiation and supernova explosions played a crucial role in shaping the galaxies, influencing the formation of subsequent generations of stars and the distribution of gas. Supernova explosions from these massive stars also enriched the surrounding gas with heavier elements. This chemical enrichment allowed for the formation of more complex molecules and played a key role in the evolution of the galaxies. As the early galaxies merged with each other, they grew larger and more structured. These mergers were common in the young universe and were a driving force behind the growth and evolution of galaxies. The process of galactic mergers was chaotic and violent, often leading to bursts of star formation. The collision of gas clouds during these mergers compressed the gas, triggering the formation of new stars at a rapid rate. Over time, these merging galaxies began to settle into more stable and organized structures. Some formed into spiral galaxies with rotating disks of stars and gas, while others became elliptical galaxies, more spherical in shape with older star populations. The influence of dark matter was crucial in the formation and evolution of early galaxies. Dark matter provided the gravitational scaffolding around which galaxies formed, helping to gather the necessary gas and driving the dynamics of galaxy formation. The first galaxies were also sites of intense radiation and energetic processes. Quasars, powered by supermassive black holes at the centers of some of these early galaxies, emitted enormous amounts of energy, influencing the surrounding gas and star formation. Observations of distant galaxies provide a glimpse into these early stages of galactic evolution. By looking at galaxies billions of light-years away, astronomers can see them as they were in the distant past, shedding light on the processes that shaped them. Advanced telescopes, such as the Hubble Space Telescope, have provided detailed images of early galaxies, revealing their shapes, sizes, and star formation activities. These observations are crucial for understanding the universe's early history. Simulations of galaxy formation help scientists model the complex interactions between gas, stars, and dark matter. These models allow researchers to test theories of galaxy formation and evolution against observational data. The formation of early galaxies set the stage for the large-scale structure of the universe. The distribution and properties of these galaxies influence the formation of galaxy clusters and the overall arrangement of galaxies in the cosmic web. The study of early galaxies continues to be a vibrant field of research. Future observations with more advanced telescopes will provide even deeper insights into the processes that govern the birth and evolution of galaxies in the young universe. Understanding the formation of early galaxies helps us piece together the broader picture of cosmic evolution. These galaxies were the building blocks of the universe's structure, and their development shaped the complex and dynamic cosmos we observe today. Galaxies come in a variety of shapes and sizes, each type with unique characteristics. The most well-known classification system is the Hubble sequence, developed by Edwin Hubble in the 1920s. Spiral galaxies are perhaps the most recognizable type. They feature a flat, rotating disk of stars, gas, and dust, with a central bulge composed mainly of older stars. The disk often contains spiral arms that are sites of active star formation. Barred spiral galaxies are a subset of spiral galaxies. They have a central bar-shaped structure composed of stars, extending from the central bulge and often connecting to the spiral arms. The Milky Way is an example of a barred spiral galaxy. Elliptical galaxies are more rounded or elongated in shape, lacking the distinct features of spiral arms. They consist mostly of older, redder stars and have little gas or dust, indicating minimal star formation activity. Elliptical galaxies range from nearly spherical, classified as E0, to highly elongated, classified as E7. They can vary significantly in size, from dwarf ellipticals with millions of stars to giant ellipticals containing trillions of stars. Lenticular galaxies serve as an intermediate type between spiral and elliptical galaxies. They have a central bulge and a disk, like spiral galaxies, but lack prominent spiral arms. Lenticular galaxies are classified as SO in the Hubble sequence. Irregular galaxies do not fit into the spiral or elliptical categories. They have no distinct shape and often appear chaotic, with scattered stars, gas, and dust. Irregular galaxies are usually rich in gas and dust, leading to active star formation. Dwarf galaxies are smaller and less luminous than typical galaxies. They can be classified as dwarf ellipticals, dwarf spheroidals, or dwarf irregulars. Despite their size, dwarf galaxies play a significant role in the structure and evolution of the universe. Peculiar galaxies have unusual shapes or features that do not fit into standard categories. These irregularities are often the result of gravitational interactions or mergers with other galaxies, leading to distorted structures. Ring galaxies are a rare type of galaxy characterized by a ring-like structure of stars and gas surrounding a central core. These rings are typically formed by the gravitational effects of a collision with another galaxy. Galaxy mergers are common events that can lead to the formation of various types of galaxies. When two galaxies collide and merge, the resulting structure can be a hybrid of their original forms or something entirely new. Starburst galaxies are defined by their exceptionally high rates of star formation. This intense activity is often triggered by interactions or mergers with other galaxies, leading to a rapid accumulation of young, massive stars. Active galactic nuclei, or AGNs, are galaxies with extremely energetic central regions. These are often powered by supermassive black holes accreting material, producing immense radiation across various wavelengths. Quasars are a type of AGN that are particularly luminous. They can outshine their host galaxies and are among the brightest objects in the universe. Quasars are essential for studying the early universe and the growth of supermassive black holes. Understanding the types of galaxies and their characteristics helps astronomers piece together the history and evolution of the universe. Each galaxy type offers unique insights into the processes that govern star formation, galactic dynamics, and cosmic structure. Mergers and interactions between galaxies are fundamental processes in the universe. These events can dramatically alter the structure and evolution of galaxies. When galaxies pass close to one another, their mutual gravitational forces cause tidal effects. These forces can distort the shapes of the galaxies, creating tidal tails and bridges of stars and gas. Galaxy mergers occur when two galaxies collide and combine to form a single, larger galaxy. This process can trigger intense bursts of star formation, known as starbursts, as gas clouds collide and compress, Major mergers involve galaxies of similar sizes. These events can transform spiral galaxies into elliptical galaxies, disrupting the original structures and mixing the stars, gas, and dust. Minor mergers involve a large galaxy absorbing a smaller one. The smaller galaxy is often disrupted and assimilated into the larger one, contributing stars and gas to the host galaxy. Interactions can also lead to the formation of tidal dwarf galaxies. These are small galaxies formed from the debris of larger galaxies during interactions, containing young stars and gas. Mergers and interactions play a crucial role in the growth of supermassive black holes. The inflow of gas during these events can fuel the black holes, leading to active galactic nuclei and quasars. Galactic collisions can induce the formation of ring galaxies. When a smaller galaxy passes through the center of a larger one, it can create a ring of star formation around the nucleus of the larger galaxy. Interacting galaxies often exhibit peculiar shapes and features. Examples include the antennae galaxies, which are in the process of merging and display long tidal tails of stars and gas. The Milky Way is currently on a collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will merge to form a single, larger galaxy, possibly an elliptical. Mergers can also strip gas from galaxies, leading to the formation of gas-poor galaxies, like ellipticals. The removal of gas inhibits new star formation, leading to older stellar populations. The study of galaxy mergers helps astronomers understand the hierarchical nature of galaxy formation. Observations and simulations show that large galaxies often form through the successive merging of smaller ones. Galaxy clusters are environments where interactions and mergers are frequent. The high density of galaxies in clusters increases the likelihood of gravitational interactions and collisions. Observing distant galaxies provides insights into the frequency and impact of mergers in the early universe. These observations help trace the growth and evolution of galaxies over cosmic time. Mergers and interactions are dynamic and complex processes that significantly influence the evolution of galaxies. They shape the structures we observe in the universe today and contribute to the ongoing story of cosmic evolution. Galactic clusters are among the largest structures in the universe. They are composed of hundreds to thousands of galaxies bound together by gravity. These clusters provide a unique environment for studying galaxy interactions and evolution. The galaxies within a cluster are diverse, including spirals, ellipticals, and irregulars. The interactions between these galaxies can lead to various phenomena, such as galaxy mergers and starbursts. The high density of galaxies in clusters makes collisions and gravitational interactions common. Clusters are not just collections of galaxies. They also contain vast amounts of hot, ionized gas. This gas emits X-rays, making clusters some of the brightest X-ray sources in the sky. The presence of this hot gas is evidence of the intense gravitational forces at work within clusters. Dark matter plays a crucial role in the structure of galactic clusters. Although it does not emit light, its gravitational influence can be detected through the motions of galaxies and the behavior of the hot gas. Dark matter makes up the majority of a cluster's mass. The center of a galaxy cluster often hosts a massive elliptical galaxy, known as the brightest cluster galaxy. These central galaxies have grown by accreting smaller galaxies over time. They are typically surrounded by a dense halo of dark matter and hot gas. Clusters can be found in various stages of evolution. Some clusters are still forming, with galaxies and subclusters merging to create larger structures. Observing clusters at different stages helps scientists understand the processes involved in their formation and growth. Gravitational lensing is a phenomenon observed in galaxy clusters. The massive gravitational field of the cluster bends and magnifies the light from background objects, creating distorted and multiple images. This effect allows astronomers to study both the cluster and distant galaxies. The study of galaxy clusters provides insights into the large-scale structure of the universe. Clusters are not randomly distributed but are found in superclusters, filaments, and voids, forming a vast cosmic web. This web reflects the distribution of dark matter on large scales. Clusters can also serve as cosmic laboratories for understanding the properties of dark energy. The growth rate of clusters over time is influenced by the expansion of the universe, which in turn is affected by dark energy. By studying clusters, scientists can gain clues about this mysterious force. The intracluster medium, the hot gas within clusters, is enriched with heavy elements. These elements were produced by stars and supernovae in the member galaxies and then expelled into the intracluster medium. This enrichment provides information about the history of star formation and supernova activity in the cluster. Galaxy clusters can also host powerful jets and lobes of radio emission from active galactic nuclei. These jets can interact with the intracluster medium, heating the gas and influencing the distribution of matter within the cluster. The dynamic environment of galaxy clusters makes them ideal for studying galaxy evolution. Galaxies in clusters can be stripped of their gas through interactions with the intracluster medium, leading to quenching of star formation and the transformation of spiral galaxies into ellipticals. Observations of clusters in different wavelengths, from X-rays to radio waves, provide a comprehensive view of their structure and composition. Each wavelength reveals different aspects of the cluster, helping to build a complete picture of these complex systems. Future observations with advanced telescopes and observatories will continue to enhance our understanding of galaxy clusters. These observations will provide deeper insights into the nature of dark matter, the history of galaxy formation, and the large-scale structure of the universe. The study of galactic clusters is essential for unraveling the mysteries of the universe. These massive structures are key to understanding the processes that shape galaxies, the role of dark matter and dark energy, and the overall evolution of the cosmos. The evolution of galaxies over time is a complex and dynamic process. It is driven by a combination of internal factors, such as star formation and supernova explosions, and external influences like galaxy mergers and interactions. In the early universe, galaxies formed from primordial gas clouds. These early galaxies were small and irregular, but they grew and evolved through mergers and accretion of gas. This hierarchical growth led to the diverse range of galaxy types we see today. Star formation is a key driver of galactic evolution. Young galaxies are often sites of intense star formation, creating new stars from the gas and dust within them. This process is most vigorous in starburst galaxies, where conditions are particularly conducive to rapid star formation. As galaxies age, their star formation rates generally decline. This decline can be due to the depletion of gas, feedback from supernovae and active galactic nuclei, or interactions with other galaxies that strip away their gas. Older galaxies typically contain more evolved, redder stars. The process of galaxy mergers plays a significant role in the evolution of galaxies. When two galaxies collide, their structures can be disrupted, leading to the formation of new stars and sometimes new galaxy types, such as elliptical galaxies from the merger of spirals. Over billions of years, galaxies undergo morphological transformations. Spiral galaxies can become ellipticals through mergers, while interactions with the intracluster medium in galaxy clusters can strip spirals of their gas, quenching star formation and transforming them into lenticular galaxies. The role of dark matter is also crucial in galactic evolution. Dark matter halos provide the gravitational framework for galaxies, influencing their formation and interactions. The distribution and behavior of dark matter affect the dynamics and growth of galaxies. Feedback processes, such as those from supernovae and active galactic nuclei, regulate star formation and the distribution of gas within galaxies. These feedback mechanisms can heat the gas, preventing it from cooling and forming new stars, and can drive outflows that shape the galaxy's structure. Galactic evolution is also influenced by environmental factors. Galaxies in clusters and groups experience more frequent interactions and mergers compared to isolated galaxies. These environments can enhance or inhibit star formation and affect the overall morphology of the galaxies. Observations of distant galaxies allow astronomers to look back in time and study the early stages of galactic evolution. These observations reveal that galaxies were smaller, more irregular, and more actively forming stars in the early universe. Simulations of galaxy formation and evolution provide insights into the processes that shape galaxies over time. These simulations incorporate the effects of dark matter, gas dynamics, star formation, and feedback, helping to explain the observed diversity of galaxies. The chemical evolution of galaxies is another important aspect. As stars evolve and die, they enrich the interstellar medium with heavy elements. This chemical enrichment affects subsequent generations of stars and the overall evolution of the galaxy. Galactic evolution is an ongoing process. Even today, galaxies continue to form stars, merge with other galaxies, and interact with their environments. The Milky Way, for example, is currently interacting with the Sagittarius dwarf galaxy and will eventually merge with the Andromeda galaxy. Future observations with more advanced telescopes will provide even deeper insights into the evolution of galaxies. By studying galaxies at various stages of development, astronomers can piece together the history of galactic evolution across cosmic time. Understanding the evolution of galaxies helps us comprehend the broader history of the universe. It reveals how the large-scale structures we see today, from galaxy clusters to the cosmic web, have formed and evolved over billions of years. Evidence for dark matter comes from several key observations in astronomy and cosmology. One of the earliest pieces of evidence was the rotation curves of spiral galaxies. When measuring the rotational speeds of stars in galaxies, it was found that the outer stars were moving much faster than expected based on the visible mass alone. This discrepancy suggests that there is additional unseen mass, or dark matter, providing the necessary gravitational pull to keep these stars in orbit. Without this extra mass, the outer stars would fly off into space. Another significant piece of evidence comes from galaxy clusters. The mass of galaxy clusters calculated from the visible light of their constituent galaxies is insufficient to account for their observed gravitational effects. Dark matter provides the additional mass needed to explain these observations. Gravitational lensing offers further evidence for dark matter. Massive objects like galaxy clusters can bend the light from background objects, creating distorted and multiple images. The amount of lensing observed often exceeds what can be accounted for by visible matter alone, indicating the presence of dark matter. The cosmic microwave background radiation also supports the existence of dark matter. Small fluctuations in this radiation, observed by missions like WMAP and Planck, provide information about the density and distribution of matter in the early universe. These observations are consistent with a universe that contains dark matter. The large-scale structure of the universe, the cosmic web of galaxies and clusters, also points to dark matter. Simulations of cosmic evolution that include dark matter match the observed distribution of galaxies far better than those that only consider visible matter. Dark matter plays a crucial role in the formation of galaxies. Without its gravitational influence, the gas in the early universe would not have been able to clump together to form stars and galaxies as quickly as it did. Bullet cluster observations provide a striking piece of evidence for dark matter. In this galaxy cluster collision, the hot gas observed in X-rays is separated from the bulk of the mass, which is inferred from gravitational lensing. This separation suggests that dark matter, which does not interact electromagnetically, passed through the collision unaffected. Dark matter is also inferred from the motions of galaxies within clusters. The velocities of these galaxies cannot be explained by the visible mass alone, indicating that additional dark matter is present to provide the necessary gravitational binding. The cosmic microwave background radiation, when analyzed in detail, shows patterns that suggest the existence of non-baryonic dark matter. This type of dark matter interacts primarily through gravity and does not emit, absorb, or reflect light, making it invisible to electromagnetic observations. Galaxy rotation curves, gravitational lensing, galaxy cluster dynamics, and the cosmic microwave background all provide independent lines of evidence for dark matter. Together, they form a compelling case for its existence, despite it being undetectable by direct observation. Efforts to detect dark matter particles directly are ongoing, with experiments deep underground designed to shield out other particles that might mimic the signals of dark matter. While no direct detection has yet been confirmed, these experiments are narrowing down the properties that dark matter particles might have. Theories and models of dark matter continue to evolve, with candidates such as WIMPs, axions, and sterile neutrinos being among the most studied. Each of these candidates has different implications for how dark matter interacts and how it might be detected. Dark matter remains one of the greatest mysteries in modern physics. Understanding its nature is crucial for a complete picture of the universe's composition and evolution. As research continues, scientists hope to uncover the true nature of this elusive substance. Dark matter in the early universe played a fundamental role in the formation of cosmic structures. Shortly after the Big Bang, the universe was hot and dense, with dark matter already present, though not yet influential on visible matter. As the universe expanded and cooled, dark matter began to dominate the gravitational landscape. Unlike normal matter, dark matter does not interact with light or electromagnetic forces, allowing it to clump together quickly under its own gravity. These clumps of dark matter formed the seeds for the large-scale structures we see today. They provided the necessary gravitational pull to attract hydrogen and helium gas, leading to the formation of the first stars and galaxies. In the early universe, dark matter was essential in overcoming the pressure of hot gas. Without its gravitational influence, the gas would have remained too diffuse to collapse into the dense regions needed to ignite star formation. The cosmic microwave background radiation offers insights into dark matter's influence during this period. Observations reveal small fluctuations in temperature and density, indicating regions where dark matter had begun to clump and influence the distribution of normal matter. These early clumps of dark matter grew over time, merging and forming larger structures. This hierarchical formation process led to the development of galaxies, galaxy clusters, and the vast cosmic web that characterizes the universe today. Dark matter's role in the early universe is also supported by computer simulations. Models that include dark matter accurately reproduce the observed distribution of galaxies and large-scale structures, highlighting its crucial role in cosmic evolution. As the first stars formed within dark matter halos, their light and radiation began to ryanize the universe. This epoch of rionization marked the end of the cosmic dark ages and further influenced the formation and growth of cosmic structures. Dark matter also played a part in the formation of supermassive black holes. The dense environments within dark matter halos provided ideal conditions for the rapid growth of these massive objects, which are found at the centers of most galaxies. The distribution of dark matter in the early universe laid the foundation for the cosmic web. Filaments of dark matter connected galaxy clusters, creating a large-scale structure that guided the formation of galaxies along these filaments. Understanding dark matter in the early universe helps scientists trace the evolution of cosmic structures from their origins to the present day. It bridges the gap between the initial conditions set by the Big Bang and the complex universe we observe now. Ongoing observations and research aim to further uncover the properties of dark matter and its impact on the early universe. By studying the distribution of galaxies and the cosmic microwave background, scientists continue to refine their models and theories. Dark matter remains elusive, but its gravitational effects are undeniable. Its presence in the early universe was crucial for shaping the cosmos, influencing everything from the formation of the first stars to the large-scale structure of the universe. Future missions and experiments, such as those using advanced telescopes and detectors, will continue to probe the nature of dark matter. These efforts aim to reveal more about its properties and interactions, offering deeper insights into its role in the universe's history. Dark matter's influence in the early universe is a testament to its importance in cosmic evolution. It remains a key focus of astrophysical research, as understanding dark matter is essential for a complete picture of the universe's past, present, and future. The influence of dark matter on structure formation in the universe is profound. Dark matter's gravitational pull was critical in shaping the early density fluctuations into the complex structures we observe today. In the early universe, small perturbations in the density of dark matter began to grow under gravity. These perturbations were the seeds for all subsequent structure formation, creating regions of higher density, where galaxies and clusters would eventually form. Dark matter halos formed around these density peaks, providing the gravitational framework for baryonic matter, or normal matter, to accumulate. These halos acted as cosmic scaffolding, guiding the distribution and growth of galaxies. As gas fell into the dark matter halos, it cooled and condensed, leading to the formation of the first stars and galaxies. Without the gravitational influence of dark matter, this process would have been much less efficient, delaying the formation of these structures. Dark matter also influenced the rate of structure formation. By enhancing gravitational attraction, it allowed structures to form more rapidly than they would have under the influence of normal matter alone. This accelerated the overall evolution of the cosmos. The hierarchical model of structure formation, where small structures merge to form larger ones, is driven by dark matter dynamics. Dark matter halos merged and grew over time, leading to the formation of larger galaxies and clusters from smaller progenitors. The distribution of dark matter is closely linked to the cosmic web, a vast network of filaments and voids that spans the universe. Galaxies are found along these filaments where dark matter density is highest, illustrating how dark matter shapes the large-scale structure of the cosmos. Gravitational lensing, where dark matter bends light from distant objects, provides direct evidence of dark matter's influence on structure formation. By studying lensing effects, astronomers can map the distribution of dark matter and understand its role in shaping cosmic structures. Dark matter's gravitational influence extends to galaxy clusters, the largest gravitationally bound structures in the universe. These clusters contain vast amounts of dark matter, which holds the galaxies within them together and influences their motions. The growth of supermassive black holes at the centers of galaxies is also linked to dark matter. The dense environments within dark matter halos provide ideal conditions for the rapid accumulation of matter onto these black holes, influencing their evolution. Observations of the cosmic microwave background reveal the imprint of dark matter on the early universe. The temperature fluctuations in the CMB reflect the initial density perturbations that grew into the large-scale structures we see today, shaped by dark matter's influence. Dark matter's role in structure formation is also crucial for understanding galaxy formation. The interactions between dark matter and baryonic matter determine the formation and evolution of galaxies, influencing their shapes, sizes, and distribution. Simulations of cosmic evolution, which include dark matter, accurately reproduce the observed large-scale structure of the universe. These simulations help researchers understand the processes driving structure formation and the role of dark matter in shaping the cosmos. Future observations and experiments will continue to refine our understanding of dark matter's influence on structure formation. By studying the distribution and behavior of dark matter, scientists aim to uncover its properties and interactions, offering deeper insights into its role in the universe. Understanding dark matter's influence on structure formation is essential for a complete picture of cosmic evolution. Its gravitational effects have shaped the universe from its earliest moments to the present day, driving the formation of galaxies, clusters, and the vast cosmic web. Detecting dark matter directly is one of the most significant challenges in modern physics. Various methods are employed to uncover the properties of this elusive substance. One primary approach is through direct detection experiments. These experiments are designed to observe the interactions between dark matter particles and normal matter. They often take place deep underground to shield them from cosmic rays and other background noise. Cryogenic detectors are a key technology in direct detection. They operate at extremely low temperatures, aiming to detect the tiny amount of heat produced when a dark matter particle collides with an atomic nucleus. Another method involves liquid noble gas detectors, such as those using xenon or argon. When dark matter particles interact with these materials, they produce scintillation light and ionization signals that can be detected and analyzed. Scientists also use bubble chambers, where superheated liquid can transition to gas in response to the energy deposited by a dark matter particle collision. This transition creates visible bubbles that can be counted and studied. Indirect detection methods focus on the byproducts of dark matter annihilation or decay. When dark matter particles annihilate each other, they can produce gamma rays, neutrinos, or other particles that can be detected with space-based and ground-based telescopes. Gamma-ray observatories like the Fermi Gamma-ray Space Telescope search for excess gamma-ray emission from regions where dark matter is expected to be dense, such as the center of our galaxy or dwarf spheroidal galaxies. Neutrino detectors, such as IceCube at the South Pole, look for high-energy neutrinos that may result from dark matter interactions. These detectors use large volumes of water or ice to capture and study neutrino signals. Gravitational lensing provides another method of detecting dark matter. By studying how dark matter bends light from distant objects, astronomers can map its distribution and infer its presence in galaxies and clusters. Large-scale surveys of galaxies and galaxy clusters help researchers study the distribution of dark matter through its gravitational effects. These surveys provide critical data for understanding the role of dark matter in cosmic structure formation. Particle accelerators, such as the Large Hadron Collider, attempt to create dark matter particles in high-energy collisions. By smashing protons together at near-light speeds, physicists hope to produce dark matter and detect its effects on the resulting particle showers. Astrophysical observations, such as the cosmic microwave background radiation, offer indirect evidence of dark matter. These observations provide information about the early universe's conditions and the influence of dark matter on cosmic evolution. Future experiments and technologies aim to improve the sensitivity of dark matter detection. Projects like the Deep Underground Neutrino experiment and the planned upgrades to existing detectors will enhance our ability to search for dark matter particles. The search for dark matter involves collaboration across multiple scientific disciplines, including particle physics, astrophysics, and cosmology. By combining data from various sources, scientists hope to build a comprehensive understanding of dark matter. Despite the challenges, the quest to detect dark matter continues to drive innovation and discovery. As technology advances and new methods are developed, the goal of uncovering the nature of dark matter comes ever closer, promising to unlock profound insights into the fundamental workings of the universe. Theories and models about dark matter aim to explain its properties and behavior. These theoretical frameworks help guide experimental searches and interpret observations. One of the leading candidates for dark matter is the WIMP, or weakly interacting massive particle. WIMPs are hypothesized to interact via the weak nuclear force, making them difficult to detect but capable of explaining the observed dark matter distribution. Axions are another theoretical candidate. These hypothetical particles are very light and interact weakly with matter. They were originally proposed to solve problems in quantum chromodynamics and have since been considered as a dark matter candidate. Sterile neutrinos are a type of neutrino that interacts even more weakly than regular neutrinos. If they exist, sterile neutrinos could account for some or all of the dark matter in the universe. The supersymmetry theory predicts the existence of partner particles for every known particle in the Standard Model. Some of these supersymmetric particles, like the neutralino, are potential dark matter candidates. The theory of extra dimensions suggests that dark matter could be a manifestation of particles interacting in higher dimensions. This idea extends the Standard Model and offers new perspectives on the nature of dark matter. Self-interacting dark matter models propose that dark matter particles can interact with each other through a new force. This interaction could explain certain observations, such as the density profiles of galaxies and galaxy clusters. Warm dark matter models propose that dark matter particles have a small but non-zero velocity. This contrasts with the cold dark matter model, where particles move very slowly. Warm dark matter could address issues related to small-scale structures in the universe. Modified Newtonian dynamics, or MOND, is an alternative theory that modifies the laws of gravity to account for the effects attributed to dark matter. While controversial, it provides a different approach to understanding galaxy rotation curves. Theories involving dark energy and dark matter interactions explore the possibility that these two mysterious components of the universe might be related. Such models aim to unify the understanding of both dark energy and dark matter. Halo models describe the distribution of dark matter in galaxies and clusters. These models use observational data to predict how dark matter is distributed and how it influences visible matter. The LCDM model, or Lambda Cold Dark Matter model, is the standard cosmological model. It includes cold dark matter and dark energy, providing a framework that explains the large-scale structure of the universe, the cosmic microwave background, and the distribution of galaxies. Simulations of cosmic structure formation rely on dark matter models to reproduce the observed universe. These simulations incorporate dark matter dynamics to predict the formation and evolution of galaxies, clusters, and the cosmic web. Alternative theories, such as emergent gravity, propose that dark matter effects are easy from modifications to gravity itself rather than from unseen particles. These theories challenge conventional models and inspire new approaches to understanding cosmic phenomena. String theory, which aims to unify all fundamental forces, predicts the existence of new particles that could be dark matter candidates. These particles, known as stringy dark matter, emerge from the complex mathematics of string theory. Ongoing research and collaboration across physics, astronomy, and cosmology are essential for refining these theories and models. Each new observation and experiment provides data that can confirm, challenge, or refine our understanding of dark matter, bringing us closer to solving one of the greatest mysteries in science. Hubble's law is a fundamental observation in cosmology that describes the relationship between the distance of galaxies and their velocity. This law states that galaxies are moving away from us at speeds proportional to their distance. Edwin Hubble discovered this relationship in the 1920s. By measuring the redshift of light from distant galaxies, he found that galaxies farther from Earth were receding faster than those closer to us. Redshift occurs because the wavelength of light stretches as the universe expands. This stretching shifts the light towards the red end of the spectrum. The greater the redshift, the faster the galaxy is moving away from us. Hubble's law is mathematically expressed as v gesture h0d, where v is the velocity of a galaxy, h0 is the Hubble constant, and d is the distance to the galaxy. The Hubble constant quantifies the rate of expansion of the universe. The discovery of Hubble's law provided strong evidence for the Big Bang theory. It showed that the universe is expanding, implying that it was once much smaller and denser. This expansion is a key feature of our current understanding of cosmology. The value of the Hubble constant has been refined over the years through various observations. Accurate measurements of the Hubble constant are crucial for understanding the age, size, and fate of the universe. Redshift measurements are obtained by observing the spectral lines of elements in galaxies. These lines shift towards longer wavelengths in more distant galaxies, providing a direct way to measure their velocities. Hubble's law applies not only to galaxies, but also to the large-scale structure of the universe. It helps cosmologists map the distribution of galaxies and understand the dynamics of cosmic expansion. The concept of redshift also leads to the idea of the cosmological redshift, which is caused by the expansion of space itself. This differs from the Doppler shift, which is due to the relative motion of objects in space. Observations of distant supernovae have been used to measure redshifts and distances, leading to the discovery of the accelerated expansion of the universe. This acceleration is attributed to dark energy, a mysterious force driving the expansion. The study of redshifts and Hubble's law has led to the development of the cosmic distance ladder. This method combines various distance measurement techniques to estimate distances to faraway galaxies, improving the accuracy of cosmological models. Hubble's law also implies that there is no center of the universe. The expansion appears uniform in all directions, meaning that every point in the universe is moving away from every other point. As telescopes and observational techniques improve, the precision of redshift measurements continues to increase. This ongoing refinement helps cosmologists test theories of the universe's expansion and its underlying mechanisms. Hubble's law and redshift are foundational concepts in cosmology. They provide a framework for understanding the large-scale structure of the universe, its expansion, and the forces that shape its evolution. Future research will continue to explore the implications of Hubble's law and redshift. By studying the universe's expansion in greater detail, scientists aim to uncover deeper insights into the nature of dark energy, the fate of the universe, and the fundamental laws of physics. Observations of distant galaxies provide a window into the early universe. By studying these galaxies, astronomers can learn about the conditions and processes that shaped the cosmos billions of years ago. Distant galaxies appear as they were when the universe was much younger, due to the finite speed of light. The further away a galaxy is, the longer its light has taken to reach us, allowing us to see back in time. Telescopes like the Hubble Space Telescope have revolutionized our understanding of distant galaxies. Hubble's deep-field images reveal thousands of galaxies, many of which formed just a few 100 million years after the Big Bang. These observations show that early galaxies were smaller and less structured than those we see today. They often appear as irregular, clumpy collections of stars and gas, indicating ongoing processes of formation and growth. Studying the light from distant galaxies allows astronomers to determine their redshifts. High redshifts indicate that these galaxies are very far away and that their light has been stretched by the expansion of the universe. Spectroscopy is a key tool in studying distant galaxies. By analyzing the spectra of these galaxies, astronomers can determine their chemical composition, star formation rates, and other physical properties. Observations of distant galaxies have revealed the presence of massive black holes even in the early universe. These black holes power quasars, which are extremely luminous and can outshine their host galaxies. Quasars provide valuable information about the early universe. Their intense light can illuminate the surrounding gas, revealing details about the intergalactic medium and the reionization process that ended the cosmic dark ages. Gravitational lensing is another important method for studying distant galaxies. Massive objects like galaxy clusters can bend and magnify the light from background galaxies, making them appear brighter and easier to study. Lens-edge galaxies offer a unique opportunity to observe details that would otherwise be too faint or small to detect. This helps astronomers study the structure and evolution of galaxies at greater distances. Infrared telescopes, like the James Webb Space Telescope, will further enhance our ability to observe distant galaxies. Infrared light can penetrate dust clouds and reveal star formation activities in regions that are otherwise obscured. Radio telescopes also play a crucial role in studying distant galaxies. They can detect emissions from cold gas, which is the raw material for star formation, providing insights into the processes that drive galaxy growth. Observations of distant galaxies contribute to our understanding of galaxy formation and evolution. They help test theoretical models and simulations, improving our knowledge of how galaxies assemble and develop over time. These observations also shed light on the large-scale structure of the universe. By mapping the distribution of distant galaxies, astronomers can study the cosmic web and the influence of dark matter and dark energy on galaxy formation. As technology advances, the study of distant galaxies will continue to provide new discoveries. Each observation brings us closer to understanding the origins and evolution of the universe, revealing the intricate processes that have shaped the cosmos over billions of years. The discovery of the accelerating expansion of the universe was a groundbreaking moment in cosmology. This unexpected finding suggested that the universe is not only expanding, but doing so at an increasing rate. The key evidence for this acceleration comes from observations of distant type Ia supernovae. These supernovae serve as standard candles because their intrinsic brightness is well understood, allowing astronomers to measure their distances accurately. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, discovered that distant supernovae were dimmer than expected. This implied that they were farther away than predicted by models of a decelerating universe. The conclusion was inescapable. The expansion of the universe is accelerating. This acceleration suggests the presence of a mysterious force, now known as dark energy, which makes up about 70% of the universe's total energy content. Dark energy is thought to have a repulsive effect, counteracting the attractive force of gravity on cosmic scales. Its exact nature remains one of the biggest mysteries in physics, with various theories proposed but none yet confirmed. The concept of a cosmological constant, introduced by Albert Einstein, has been revived to explain dark energy. The cosmological constant represents a constant energy density filling space homogeneously. In this context, it acts as a form of dark energy driving the acceleration. Other theories propose that dark energy might be a dynamic field, varying over time and space. These models, known as quintessence, suggest that dark energy could change its properties as the universe evolves. The discovery of accelerating expansion has profound implications for the fate of the universe. If the expansion continues to accelerate, galaxies will eventually move away from each other so rapidly that distant galaxies will become unreachable, and the universe will grow increasingly dark and cold. The acceleration affects the large-scale structure of the universe. It influences the formation and growth of cosmic structures, altering the way galaxies and clusters evolve over time. Observations of the cosmic microwave background provide additional evidence for accelerating expansion. The detailed measurements of the CMB's fluctuations are consistent with a universe dominated by dark energy. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey, map the distribution of galaxies across vast distances. These maps help scientists understand how dark energy influences the universe's expansion and structure. Gravitational lensing studies also contribute to our understanding of dark energy. By analyzing the bending of light from distant galaxies, astronomers can infer the distribution of dark matter and the effects of dark energy on the universe's geometry. Future missions, like the European Space Agency's Euclid spacecraft and NASA's Wide Field Infrared Survey Telescope, aim to explore dark energy further. These missions will provide more precise measurements of cosmic expansion and the distribution of dark matter. Understanding the accelerating expansion of the universe is a top priority in modern cosmology. The quest to uncover the nature of dark energy involves combining observations from various wavelengths and techniques, bringing us closer to solving one of the most profound mysteries in science. The discovery of accelerating expansion has revolutionized our view of the cosmos. It highlights how much we still have to learn about the universe and drives ongoing efforts to unravel the fundamental forces shaping our cosmic destiny. Dark energy is one of the most intriguing concepts in cosmology. It is hypothesized to be a form of energy that permeates all of space and is responsible for the accelerated expansion of the universe. Unlike dark matter, which interacts through gravity, dark energy appears to have a repulsive effect. It counteracts the attractive force of gravity, causing the expansion of the universe to speed up over time. The concept of dark energy was introduced to explain observations of distant supernovae that indicated the universe's expansion is accelerating. This discovery challenged previous models that suggested the expansion should be slowing down due to gravitational attraction. One possible explanation for dark energy is the cosmological constant, a term originally introduced by Einstein in his equations of general relativity. The cosmological constant represents a constant energy density filling space uniformly. If dark energy is indeed a cosmological constant, it implies that the energy density of the vacuum remains constant over time, even as the universe expands. This would mean that dark energy's influence grows stronger as the universe becomes more dilute. Another theory suggests that dark energy could be a dynamic field, similar to a scalar field. This idea, known as quintessence, proposes that the properties of dark energy could change over time, potentially influencing the universe's fate differently than a cosmological constant. Observations of the cosmic microwave background, galaxy clusters, and large-scale structure provide indirect evidence for dark energy. These observations help constrain its properties and guide theoretical models. Dark energy makes up about 70% of the total energy content of the universe, dwarfing the contributions from dark matter and ordinary matter. Understanding its nature is crucial for a complete picture of the cosmos. The influence of dark energy on the universe's expansion can be seen in the Hubble constant, which measures the rate of expansion. Precise measurements of the Hubble constant help scientists understand the balance between dark energy and other components of the universe. Dark energy also affects the geometry of the universe. Its repulsive force causes space to stretch, influencing the paths of light and the formation of large-scale structures. This stretching effect is observable in the cosmic microwave background and the distribution of galaxies. Future observations and experiments aim to explore dark energy in more detail. Missions like Euclid and the James Webb Space Telescope will provide new data on cosmic expansion and the behavior of dark energy over time. Understanding dark energy is not only a challenge for cosmology, but also for fundamental physics. It may require new theories or modifications to general relativity to fully explain its properties and effects. The discovery of dark energy has profound implications for the ultimate fate of the universe. If dark energy remains constant or increases, the universe could continue to expand forever, leading to a cold, dark, and isolated future. Alternatively, if dark energy changes over time, it could lead to different scenarios, such as a big rip, where the expansion becomes so extreme that galaxies, stars, and even atoms are torn apart. The study of dark energy is a vibrant field of research. It combines observational astronomy, theoretical physics, and advanced computational models to uncover the mysteries of this enigmatic force driving the universe's accelerated expansion. Dark energy remains one of the most significant and least understood components of the universe. As research progresses, it promises to reveal new insights into the nature of space, time, and the fundamental forces that govern the cosmos. Current research into dark energy involves a combination of observational, experimental, and theoretical approaches. Scientists are striving to better understand its properties and how it influences the cosmos. Observationally, large-scale surveys of the universe are essential. Projects like the Dark Energy Survey map the distribution of galaxies to study how dark energy affects their clustering and growth over time. The Euclid mission, launched by the European Space Agency, aims to understand the nature of dark energy by observing the geometry of the universe. It will measure the shapes and distances of billions of galaxies, providing critical data on cosmic expansion. The James Webb Space Telescope will also contribute to dark energy research. Its infrared capabilities will allow it to peer further back in time, observing the earliest galaxies and the impact of dark energy on their formation and evolution. Ground-based observatories, like the Large Synoptic Survey Telescope, will provide high-resolution images of the night sky. These images help track changes in galaxy positions and shapes, shedding light on dark energy's effects. Gravitational wave detectors such as LIGO and Virgo offer another avenue of exploration. By studying the universe's expansion through the lens of gravitational waves, scientists hope to gain new insights into dark energy. Theoretical physicists are developing new models to explain dark energy. Some propose modifications to general relativity, suggesting that our understanding of gravity might need revision to account for cosmic acceleration. Quintessence models suggest that dark energy could be a dynamic field with properties that change over time. These models are tested against observational data to see if they can explain the observed acceleration of the universe. Some researchers explore the possibility of extra dimensions influencing dark energy. String theory and other higher dimensional theories propose that dark energy could result from interactions in these unseen dimensions. The concept of interacting dark energy involves scenarios where dark energy might exchange energy with dark matter. These interactions could provide clues about the nature of both dark components of the universe. Alternative gravity theories, such as FR gravity or scalar tensor theories, offer different explanations for cosmic acceleration. These theories modify the equations of general relativity to produce effects similar to dark energy. Cosmic voids, large empty spaces between galaxy clusters, provide a natural laboratory for studying dark energy. Observations of how galaxies move around these voids help constrain dark energy models. Current experiments like DESI, Dark Energy Spectroscopic Instrument, will map the 3D distribution of galaxies to measure the expansion history of the universe. This detailed map will improve our understanding of dark energy's role over cosmic time. Simulations of the universe, incorporating dark energy, allow researchers to predict how different models will affect the large-scale structure. These simulations help interpret observational data and refine theoretical models. Collaborative efforts across disciplines and continents are crucial in dark energy research. By combining expertise in observational astronomy, theoretical physics, and computational modeling, scientists aim to unlock the secrets of this mysterious force. As research progresses, the ultimate goal is to integrate dark energy into a unified theory of the universe. Understanding dark energy will not only solve one of cosmology's biggest mysteries, but also potentially revolutionize our comprehension of fundamental physics and the nature of reality. The cosmic web is a vast network of interconnected structures that make up the large-scale organization of matter in the universe. It consists of galaxies, galaxy clusters, and intergalactic gas, all linked by filaments of dark matter. These filaments are the largest known structures in the cosmos, stretching across hundreds of millions of light-years. They form a web-like pattern that connects dense nodes of matter where galaxies and clusters are located. The cosmic web was formed through the gravitational collapse of matter over billions of years. Dark matter played a crucial role in this process, providing the gravitational pull needed to draw ordinary matter into these filamentary structures. Observations of the cosmic web are made using various techniques, including galaxy surveys and gravitational lensing. These methods allow astronomers to map the distribution of matter on the largest scales. The filaments of the cosmic web are not uniform. They vary in density and composition, containing vast amounts of dark matter and intergalactic gas. This gas is often heated to high temperatures, making it detectable in X-ray observations. Within the filaments, galaxies form and evolve. The dense environments can trigger star formation and influence the growth of galaxies, leading to the rich variety of galactic structures observed today. Galaxy clusters, the most massive structures in the universe, are found at the intersections of these filaments. These nodes act as gravitational hubs, drawing in matter from the surrounding filaments and enhancing their mass and complexity. The study of the cosmic web provides insights into the fundamental processes of cosmic evolution. By understanding how matter is distributed on these large scales, scientists can learn about the underlying physics governing the universe. Cosmic web simulations, which model the distribution and evolution of matter, are essential tools for this research. They help predict how the web should look, based on different cosmological models, and compare these predictions with observations. The intergalactic medium, the space between galaxies within the filaments, is a crucial component of the cosmic web. It contains the majority of the universe's baryonic matter and plays a key role in the cycling of gas into and out of galaxies. The cosmic web also influences the motion of galaxies. Galaxies tend to move along the filaments towards the densest regions, a process known as cosmic flow. This movement can affect galaxy interactions and mergers. Dark matter is the backbone of the cosmic web. Its gravitational influence shapes the distribution of ordinary matter, guiding the formation of structures from the smallest galaxies to the largest clusters. Observations of the cosmic microwave background provide evidence for the initial conditions that led to the formation of the cosmic web. Tiny fluctuations in the early universe grew into the large-scale structures we see today. The cosmic web is a dynamic structure, constantly evolving as galaxies form, merge, and move within it. Studying this evolution helps scientists understand the history and future of the universe. The intricate pattern of the cosmic web reveals the interconnectedness of all matter in the universe. It highlights the role of dark matter in shaping the cosmos and provides a framework for understanding the large-scale structure of the universe. Superclusters are among the largest structures in the universe. They consist of groups of galaxy clusters bound together by gravity, forming vast regions of the cosmic web. These superclusters can span hundreds of millions of light-years, containing thousands of galaxies. They represent the densest regions of the universe and are key to understanding the large-scale structure of the cosmos. The formation of superclusters began shortly after the Big Bang. Small density fluctuations in the early universe grew over time, drawing in matter through gravitational attraction and forming these massive structures. Within superclusters, galaxy clusters are the primary components. These clusters contain hundreds to thousands of galaxies, along with hot gas and dark matter, bound together by gravity. The Sloan Great Wall is one of the most well-known superclusters. It stretches over 1.37 billion light-years, making it one of the largest known structures in the universe. Voids are the opposite of superclusters. These vast, empty regions of space contain very few galaxies and represent the most underdense areas of the universe. Voids can be as large as superclusters, spanning hundreds of millions of light-years. The existence of voids creates a contrast with the dense regions of superclusters, contributing to the overall cosmic web structure. The distribution of voids and superclusters helps map the large-scale organization of the universe. Voids are not entirely empty. They contain dark matter and some intergalactic gas, but the density is much lower than in superclusters. The few galaxies that do exist in voids are often isolated and have unique properties compared to those in denser regions. The study of voids helps astronomers understand the distribution of matter in the universe. By analyzing the properties of voids, researchers can gain insights into the nature of dark energy and the overall geometry of the cosmos. Superclusters and voids provide a framework for studying cosmic evolution. They reveal how matter has clustered and expanded over billions of years, influenced by gravity, dark matter, and dark energy. The interaction between superclusters and voids affects the motion of galaxies. Galaxies tend to move from voids towards the denser regions of superclusters, a process that shapes the dynamics of the universe. Observations of superclusters and voids are made using large-scale galaxy surveys and cosmic microwave background measurements. These observations help create detailed maps of the universe's structure. Simulations of the universe, incorporating dark matter and dark energy, accurately reproduce the observed distribution of superclusters and voids. These simulations are essential for testing cosmological models. The largest known supercluster is the Hercules Corona Borealis Great Wall, which spans over 10 billion light-years. Discoveries like this continue to push the boundaries of our understanding of the universe's size and complexity. Understanding superclusters and voids is crucial for a complete picture of the universe. They represent the extremes of cosmic structure, from the densest regions to the emptiest voids, highlighting the vast and varied nature of the cosmos. Observational techniques in astronomy have evolved significantly, enabling us to explore the universe in unprecedented detail. These techniques allow scientists to study everything from nearby planets to the most distant galaxies. One of the primary tools in observational astronomy is the optical telescope. Optical telescopes collect and magnify visible light from celestial objects, allowing detailed observations of stars, galaxies, and other phenomena. Radio telescopes detect radio waves emitted by celestial objects. These telescopes can observe areas of space obscured by dust in visible light, revealing phenomena such as pulsars, quasars, and the cosmic microwave background. Infrared telescopes are designed to detect infrared radiation, which can penetrate dust clouds that block visible light. This capability is essential for studying star formation regions and the centers of galaxies. Space telescopes, like the Hubble Space Telescope, avoid the distortion caused by Earth's atmosphere, providing clearer and more detailed images of the cosmos. Space-based observatories can operate across a range of wavelengths, from ultraviolet to infrared. Spectroscopy is a technique used to analyze the light from celestial objects. By spreading light into its component colors, astronomers can determine the composition, temperature, velocity, and other properties of stars and galaxies. Gravitational lensing occurs when the gravity of a massive object, like a galaxy cluster, bends and magnifies the light from objects behind it. This phenomenon allows astronomers to study very distant galaxies and dark matter distributions. Adaptive optics is a technology that compensates for the distortion caused by Earth's atmosphere in real time. This technique enhances the resolution of ground-based telescopes, allowing them to produce images comparable to those taken from space. Interferometry involves combining the signals from multiple telescopes to create a single image with higher resolution. This technique is used in radio astronomy and increasingly in optical and infrared astronomy. Photometry measures the brightness of celestial objects over time. This technique is crucial for studying variable stars, exoplanets, and other transient phenomena in the universe. Transit photometry detects exoplanets by measuring the slight dimming of a star's light when a planet passes in front of it. This method has led to the discovery of thousands of exoplanets, expanding our understanding of planetary systems. Astrometry is the precise measurement of the positions and motions of celestial objects. This technique helps determine the distances to stars, the orbits of planets, and the dynamics of star clusters and galaxies. High-energy telescopes observe gamma rays and X-rays emitted by some of the most energetic processes in the universe, such as supernovae, black holes, and neutron stars. These observations provide insights into the extreme conditions in space. Time-domain astronomy involves studying celestial objects that change over time, such as supernovae, variable stars, and active galactic nuclei. This field relies on continuous monitoring to capture transient events. Gravitational wave observatories, like LIGO and Virgo, detect ripples in space-time caused by massive accelerating objects, such as merging black holes and neutron stars. These observations open a new window into understanding the universe's most violent events. By combining multiple observational techniques, astronomers can build a comprehensive picture of the universe. Each method provides unique insights, contributing to a deeper understanding of cosmic phenomena and the fundamental laws governing the cosmos. Computer simulations are a powerful tool in modern astrophysics. They allow scientists to model and understand complex processes in the universe that are difficult or impossible to observe directly. Simulations can recreate the conditions of the early universe, tracing the formation and evolution of galaxies from the Big Bang to the present day. These models help scientists test theories about cosmic evolution and the role of dark matter and dark energy. One of the most well-known simulations is the Millennium Simulation. It models the formation of large-scale structures in the universe, incorporating the effects of dark matter and dark energy on the distribution of galaxies and galaxy clusters. Simulations can also explore the dynamics of individual galaxies. By modeling the gravitational interactions between stars, gas, and dark matter, scientists can study the formation of spiral arms, galactic collisions, and the growth of supermassive black holes. Hydrodynamic simulations add the behavior of gas and fluids to the models, allowing researchers to study star formation, supernova explosions, and the interstellar medium. These simulations are essential for understanding the life cycles of stars and the evolution of galaxies. Cosmological simulations require vast computational resources. Supercomputers, capable of performing quadrillions of calculations per second, are used to run these models, often taking weeks or months to complete a single simulation. The Illustrious project is another example of a large-scale simulation. It models the formation and evolution of galaxies, incorporating complex physics such as star formation, black hole growth, and feedback from supernovae and active galactic nuclei. Simulations also play a crucial role in studying dark matter. By modeling how dark matter interacts with itself and with normal matter, researchers can predict its distribution and compare these predictions with observations. Simulations of galaxy clusters help scientists understand the interactions between galaxies and the intra-cluster medium. These models can reveal how gas is stripped from galaxies, how it cools and forms new stars, and how clusters evolve over time. In the field of exoplanet research, simulations help predict the atmospheres and climates of distant worlds. By modeling the effects of a planet's atmosphere, rotation, and orbital parameters, scientists can infer the potential for habitability. Simulations of the cosmic microwave background radiation allow researchers to test different cosmological models. By comparing simulated CMB maps with real observations, scientists can refine their understanding of the universe's early conditions and its subsequent evolution. Gravitational wave simulations model the mergers of black holes and neutron stars. These models predict the waveforms of gravitational waves, helping researchers identify and analyze the signals detected by observatories like LIGO and Virgo. Simulations also aid in the study of the large-scale structure of the universe. By modeling the distribution of galaxies and dark matter, researchers can understand the formation of the cosmic web and the influence of dark energy on its expansion. Virtual observatories created through simulations allow scientists to test observational strategies and instrument designs before actual deployment. This practice helps optimize the performance of telescopes and detectors, ensuring better data quality. The future of astrophysical simulations lies in increasing complexity and resolution. As computational power grows, simulations will incorporate more detailed physics, larger volumes of space, and finer scales, providing even deeper insights into the universe's workings. Computer simulations are an indispensable part of astrophysical research. They complement observations, test theories, and provide a deeper understanding of the fundamental processes that shape the cosmos. Through simulations, scientists can explore the universe in ways that are not possible with observations alone. The impact of dark matter and dark energy on cosmic evolution is profound. These mysterious components have shaped the universe from its earliest moments to its current state. Dark matter played a crucial role in the formation of the first structures in the universe. Its gravitational pull helped matter clump together, forming the seeds of galaxies and clusters that we observe today. Without dark matter, the universe would look vastly different. The normal matter alone wouldn't have been able to form structures quickly enough, delaying the formation of galaxies, stars, and planets. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe. Its repulsive force counteracts the attractive force of gravity, causing the expansion rate to increase over time. This accelerating expansion influences the fate of the universe. If dark energy continues to dominate, the universe will keep expanding at an ever-increasing rate, leading to a cold, dark, and isolated future. The interplay between dark matter and dark energy affects the large-scale structure of the cosmos. Dark matter clumps into halos, forming the backbone of the cosmic web, while dark energy drives the expansion of the spaces between these structures. Galaxies and galaxy clusters form at the nodes of this cosmic web, where dark matter density is highest. The distribution of these structures gives us clues about the nature and properties of dark matter and dark energy. Dark matter also affects the internal dynamics of galaxies. It provides the additional mass needed to explain the rotation curves of galaxies, which show that stars at the edges of galaxies move faster than expected, based on visible matter alone. Dark energy's influence on cosmic evolution is observed in the cosmic microwave background radiation. The detailed measurements of the CMB reveal how dark energy has shaped the geometry and expansion history of the universe. The presence of dark matter and dark energy has led to the development of the LCDM model, the standard model of cosmology. This model describes a universe composed of dark energy, dark matter, and normal matter, providing a framework for understanding cosmic evolution. Simulations of cosmic evolution that include dark matter and dark energy accurately reproduce the observed distribution of galaxies and large-scale structures. These simulations help test and refine cosmological theories. Observations of distant supernovae and galaxy clusters also provide evidence for the accelerating expansion driven by dark energy. These observations are crucial for understanding the current and future state of the universe. The impact of dark matter and dark energy extends to the smallest scales as well. Dark matter influences the formation of stars and planetary systems, while dark energy affects the dynamics of galaxies and clusters. The study of dark matter and dark energy continues to be a major focus in astrophysics. Ongoing observations, simulations, and theoretical research aim to uncover the true nature of these mysterious components and their impact on the universe. Understanding the impact of dark matter and dark energy on cosmic evolution is essential for a complete picture of the universe. These components have shaped the cosmos from its earliest moments, influencing the formation and behavior of all cosmic structures we observe today. Black holes are formed when massive stars collapse under their own gravity. This collapse occurs at the end of a star's life cycle, typically after it has exhausted its nuclear fuel. When a massive star runs out of fuel, it can no longer support itself against gravitational collapse. The core implodes, and if the remaining mass is above a certain threshold, it forms a black hole. Stellar mass black holes, the most common type, result from the collapse of stars with masses greater than about 20 times that of the Sun. The core's collapse creates a singularity, a point of infinite density surrounded by an event horizon. The event horizon is the boundary beyond which nothing can escape the black hole's gravitational pull. It marks the limit where the escape velocity equals the speed of light. Supermassive black holes with masses ranging from millions to billions of times the mass of the Sun are found at the centers of most galaxies. Their formation processes are still not fully understood, but they likely grew through the accretion of gas and mergers with other black holes. Intermediate mass black holes, with masses between stellar mass and supermassive black holes, are harder to detect. They may form through the mergers of smaller black holes, or the direct collapse of massive gas clouds. Primordial black holes are a hypothetical class that could have formed in the early universe due to high-density fluctuations. If they exist, they could provide insights into the conditions of the early universe. Black holes can grow by accreting matter from their surroundings. This accretion process forms an accretion disk, where matter spirals inwards, heating up and emitting intense radiation, often observed in X-rays. In binary systems, a black hole can draw material from a companion star. This process can lead to the emission of X-rays and other radiation, making the black hole detectable despite its invisible nature. Merging black holes create gravitational waves, ripples in space-time that can be detected by observatories like LIGO and Virgo. These detections provide direct evidence of black hole mergers and offer new insights into their properties. The formation of black holes is influenced by the initial mass and composition of the progenitor star, as well as its environment. Stars in dense star clusters, or those with binary companions, have different evolutionary paths leading to black hole formation. Theoretical models and simulations help scientists understand the complex processes involved in black hole formation. These models incorporate the physics of stellar evolution, supernova explosions, and gravitational collapse. Observations of black holes and their environments provide critical tests for these models. By studying the properties and behaviors of black holes, astronomers can refine their theories and gain a deeper understanding of these enigmatic objects. The study of black holes extends beyond their formation. Their extreme gravitational fields offer unique laboratories for testing the laws of physics, particularly general relativity, under conditions that cannot be replicated on Earth. Black holes play a significant role in the evolution of galaxies and the universe. Their interactions with surrounding matter and their gravitational influence shape the formation and behavior of cosmic structures on all scales. Understanding the formation and growth of black holes is a key aspect of modern astrophysics. It connects stellar evolution, gravitational physics, and cosmology, providing a comprehensive view of some of the most powerful and mysterious objects in the universe. Black holes come in various types and sizes, each with unique characteristics. The three primary types are stellar mass black holes, supermassive black holes, and intermediate mass black holes. Stellar mass black holes are the most common, formed from the remnants of massive stars. They typically have masses ranging from about 3 to several tens of times the mass of the Sun. These black holes often exist in binary systems, where they can interact with companion stars. The gravitational pull of the black hole can strip material from the companion, forming an accretion disk that emits X-rays and other radiation. Supermassive black holes reside at the centers of most galaxies, including our Milky Way. Their masses range from millions to billions of times that of the Sun, significantly influencing their host galaxies' dynamics and evolution. The formation of supermassive black holes is still not entirely understood. They may grow through the accretion of gas, mergers with other black holes, and the collapse of massive gas clouds in the early universe. Intermediate mass black holes are thought to have masses between 100 and several 100,000 times that of the Sun. These black holes might form through the mergers of smaller black holes or direct collapse in dense star clusters. Primordial black holes are a hypothetical class that could have formed soon after the Big Bang due to high-density fluctuations. If they exist, they could provide valuable insights into the conditions of the early universe and the nature of dark matter. The event horizon of a black hole is the boundary beyond which nothing can escape its gravitational pull. It marks the point where the escape velocity exceeds the speed of light, rendering the black hole invisible. The size of the event horizon, also known as the Schwarzschild radius, depends on the black hole's mass. For stellar mass black holes, this radius is only a few kilometers, while for supermassive black holes, it can be as large as the solar system. Inside the event horizon lies the singularity, a point of infinite density where the laws of physics as we know them break down. The singularity is hidden from view by the event horizon, making it one of the most mysterious aspects of black holes. Black holes can spin, and this rotation affects their properties. Rotating black holes, or Kerr black holes, have more complex structures than non-rotating, or Schwarzschild black holes. The spin can influence the shape of the event horizon and the dynamics of the accretion disk. Hawking radiation is a theoretical prediction that black holes can emit radiation due to quantum effects near the event horizon. This radiation causes black holes to lose mass over time, potentially leading to their evaporation in the distant future. The discovery of gravitational waves has opened a new way to study black holes. Mergers of black holes produce these waves, allowing scientists to detect and analyze the properties of black holes that would otherwise be hidden. The characteristics of black holes, such as mass, spin, and charge, determine their effects on surrounding matter and space-time. These properties influence everything from the formation of jets and accretion disks to the bending of light and the creation of gravitational waves. Understanding the types and characteristics of black holes is crucial for a comprehensive view of the universe. These enigmatic objects challenge our understanding of physics, offering unique insights into the nature of gravity, quantum mechanics, and the fundamental structure of space-time. Quasars are among the most luminous and energetic objects in the universe. They are powered by supermassive black holes at the centers of galaxies, which accrete matter at incredibly high rates. The intense gravitational forces around these black holes cause the infalling material to heat up and emit vast amounts of radiation. This process creates a quasar, which can outshine the combined light of all the stars in its host galaxy. Quasars were first discovered in the 1960s through their radio emissions, but it soon became clear that they emit across the entire electromagnetic spectrum, including visible light, ultraviolet, X-rays, and gamma rays. The energy output of a quasar is driven by an accretion disk of gas and dust spiraling into the supermassive black hole. Magnetic fields within the disk can also drive powerful jets of particles that extend far beyond the host galaxy. These jets can travel millions of light-years, affecting the intergalactic medium and even neighboring galaxies. The interactions between quasar jets and their surroundings play a significant role in galaxy evolution. Quasars are crucial for understanding the early universe. They are so bright that they can be seen at great distances, acting as beacons that allow astronomers to study the conditions of the universe billions of years ago. The light from distant quasars passes through intervening clouds of gas, absorbing specific wavelengths and creating absorption lines in the quasar's spectrum. By analyzing these lines, astronomers can learn about the composition and distribution of matter in the early universe. Quasars also provide insights into the growth of supermassive black holes. The mass of a quasar's black hole can be estimated from the properties of the accretion disk and the velocity of the surrounding gas. The relationship between quasars and their host galaxies is complex. The energy and radiation from a quasar can influence star formation rates and the dynamics of the host galaxy, often leading to feedback processes that regulate the growth of both the black hole and the galaxy. Observations of quasars have revealed the presence of supermassive black holes in the centers of most large galaxies. This suggests a coevolution of black holes and galaxies, with quasars playing a key role in this process. Quasars can also serve as cosmic distance markers. Their brightness and characteristic light curves make them useful for measuring distances in the universe, contributing to our understanding of cosmic expansion. The study of quasars continues to evolve with new observations from advanced telescopes and instruments. High-resolution imaging and spectroscopy provide detailed views of quasar environments, shedding light on the complex physics at play. The discovery of gravitational waves from merging supermassive black holes in quasar systems would provide a new way to study these enigmatic objects and their impact on galaxy formation and evolution. Quasars are also linked to the rionization of the universe. The intense ultraviolet radiation from quasars likely contributed to rionizing the hydrogen in the early universe, ending the cosmic dark ages and allowing light to travel freely. Understanding the role of quasars in cosmic evolution helps piece together the history of the universe. These powerful objects offer a unique window into the processes that shaped galaxies and their central black holes, revealing the dynamic interplay between matter, energy, and gravity on the largest scales. Observational evidence for the existence and characteristics of quasars comes from a variety of methods and instruments. These observations have significantly expanded our understanding of these powerful objects. One of the earliest pieces of evidence for quasars was their strong radio emissions. When first discovered, these sources appeared star-like, but their radio brightness was far too great to be ordinary stars. Optical telescopes later revealed that quasars exhibit high redshifts, indicating that they are incredibly distant and that their light has traveled billions of years to reach us. This implies that quasars are among the earliest objects in the universe. Spectroscopy has provided detailed information about quasars. Their spectra show broad emission lines, which are signatures of fast-moving gas in the accretion disks around supermassive black holes. Quasars are observed across the entire electromagnetic spectrum, from radio waves to gamma rays. This multi-wavelength observation is crucial because it helps scientists understand the various processes occurring in and around quasars. X-ray observations, for example, reveal the high-energy environment close to the supermassive black hole. Space telescopes like Chandra and XMM Newton have provided invaluable data on the X-ray emissions from quasars. Infrared observations penetrate dust that can obscure quasars in visible light. The Spitzer Space Telescope and other infrared observatories have uncovered many quasars hidden behind thick dust clouds. Gravitational lensing, where the gravity of a massive object like a galaxy bends the light from a more distant quasar, has provided a unique way to study quasars. Lensed quasars appear as multiple images, offering detailed information about both the quasar and the lensing object. Polarization studies of quasar light have revealed the presence of magnetic fields and the alignment of particles in the jets emitted by quasars. This information helps scientists understand the role of magnetic fields in quasar dynamics. Quasar variability is another important area of observation. Quasars can change brightness over days, months, or years, providing clues about the processes in the accretion disk and the black hole's immediate environment. The Sloan Digital Sky Survey has catalogued hundreds of thousands of quasars, providing a comprehensive database for studying their properties and distribution across the universe. This large sample size allows for statistical studies of quasar evolution. High-resolution imaging with instruments like the Hubble Space Telescope has resolved the host galaxies of quasars, revealing interactions and mergers that may trigger quasar activity. These images provide context for the environments in which quasars form and evolve. Radio interferometry, which combines signals from multiple radio telescopes, has mapped the detailed structure of quasar jets. These observations show how jets interact with the intergalactic medium and influence their surroundings. The connection between quasars and galaxy evolution is evident from observations showing that quasar activity often coincides with periods of intense star formation in their host galaxies. This suggests a link between black hole growth and galaxy evolution. Future observatories, such as the James Webb Space Telescope, will provide even more detailed observations of quasars. These new instruments will offer unprecedented resolution and sensitivity, uncovering new aspects of quasar physics. Overall, the observational evidence for quasars paints a comprehensive picture of these extraordinary objects. By studying them across different wavelengths and over time, astronomers continue to unravel the mysteries of quasars and their role in the universe. Gamma-ray bursts are among the most energetic events in the universe. They release a tremendous amount of energy in the form of gamma rays, often outshining entire galaxies for brief periods. These bursts are classified into two main types: long-duration and short-duration gamma-ray bursts. Long-duration bursts last more than 2 seconds and are typically associated with the collapse of massive stars. Short-duration bursts last less than 2 seconds and are linked to the mergers of neutron stars. Long-duration gamma-ray bursts are thought to occur when a massive star exhausts its nuclear fuel and collapses into a black hole. This collapse triggers a supernova explosion and produces a jet of material moving at nearly the speed of light. Short-duration gamma-ray bursts are believed to result from the collision of 2 neutron stars or a neutron star and a black hole. These mergers produce intense gravitational waves and gamma-ray emissions. Observations of gamma-ray bursts come from space-based telescopes, as Earth's atmosphere absorbs gamma rays. Satellites like NASA's Swift and Fermi observatories have detected and localized thousands of gamma-ray bursts. The afterglows of gamma-ray bursts, which can be observed in X-ray, optical, and radio wavelengths, provide valuable information about the environment surrounding these explosions. Afterglows help astronomers pinpoint the location of the bursts and study the properties of the progenitor stars. Gamma-ray bursts are important for studying the early universe. Some bursts occur at very high redshifts, indicating that they happened when the universe was young. These distant bursts provide insights into the formation of the first stars and galaxies. The extreme energy of gamma-ray bursts can affect their surroundings. The intense radiation can ionize gas in the host galaxy, influencing star formation and the evolution of the galaxy. Gamma-ray bursts also serve as natural laboratories for studying relativistic jets. The jets produced during these bursts are highly collimated and travel at near light speeds, providing a testbed for theories of jet formation and particle acceleration. The detection of gravitational waves from neutron star mergers, along with gamma-ray bursts, has opened a new era of multi-messenger astronomy. This combination of gravitational and electromagnetic signals offers a more complete picture of these cataclysmic events. Gamma-ray bursts can be used as probes of the intergalactic medium. As the gamma rays travel through space, they interact with the matter and radiation they encounter, providing information about the composition and structure of the universe. The study of gamma-ray bursts has led to significant advancements in our understanding of stellar evolution, black hole formation, and high-energy astrophysics. These bursts are among the most energetic and dynamic phenomena observed in the universe. Future missions, such as the SVOM satellite and the proposed gamma-ray burst polarimeter, aim to further our understanding of gamma-ray bursts. These missions will provide more detailed observations and help answer remaining questions about the nature of these powerful events. Gamma-ray bursts also have implications for the search for life in the universe. The intense radiation from nearby bursts could sterilize planets, impacting the habitability of regions within galaxies. Theoretical models continue to evolve as new data from gamma-ray bursts are collected. These models help scientists understand the mechanisms driving these bursts and their impact on the universe. Gamma-ray bursts are a reminder of the violent and dynamic nature of the cosmos. They provide a window into the most extreme conditions in the universe, helping us understand the fundamental processes that shape our cosmic environment. Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe. They were first predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. The first direct detection of gravitational waves was made in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This groundbreaking discovery confirmed a key prediction of Einstein's theory and opened a new era of astronomy. Gravitational waves are generated by the acceleration of massive objects. The most common sources include merging black holes, merging neutron stars, and supernova explosions. These waves travel at the speed of light, carrying information about their origins. LIGO and its European counterpart Virgo use laser interferometry to detect these tiny ripples in space-time. The detectors are designed to measure changes in distance smaller than 1,000th of the diameter of a proton. When gravitational waves pass through the detectors, they cause minute changes in the lengths of the interferometer arms. By analyzing these changes, scientists can infer the properties of the waves and their sources. The first detected gravitational wave event, GW150914, was caused by the merger of two black holes about 1.3 billion light-years away. This event provided the first direct evidence of binary black hole systems. Gravitational waves offer a new way to observe the universe. Unlike electromagnetic waves, they are not absorbed or scattered by matter, allowing them to carry information from the most extreme and hidden regions of the cosmos. Multi-messenger astronomy combines gravitational wave data with electromagnetic observations, such as light, radio waves, and X-rays. This approach provides a more comprehensive understanding of cosmic events. The detection of gravitational waves from neutron star mergers, like GBM 70817, has provided insights into the production of heavy elements. The collision of neutron stars produces kilonovae, which release elements such as gold and platinum into space. Gravitational waves also provide a way to test the fundamental laws of physics. They offer a unique laboratory for studying general relativity in the strong field regime, where gravitational forces are extreme. Observations of gravitational waves can help determine the rate of expansion of the universe, known as the Hubble constant. By measuring the distances and redshifts of gravitational wave sources, scientists can refine estimates of this important cosmological parameter. Future gravitational wave observatories, such as the space-based LISA mission, will expand our ability to detect these waves. LISA will be sensitive to lower frequency waves, allowing the detection of mergers involving supermassive black holes and other exotic objects. Pulsar timing arrays are another method for detecting gravitational waves. These arrays monitor the timing of pulses from millisecond pulsars, looking for slight variations caused by passing gravitational waves. Gravitational waves have the potential to reveal new and unexpected phenomena. As detection methods improve and more events are observed, scientists anticipate discovering sources and processes that were previously unknown. The study of gravitational waves is revolutionizing our understanding of the universe. These waves provide a new way to observe and explore the cosmos, offering insights into the most powerful and mysterious forces in nature. As we continue to detect and study these waves, we gain a deeper understanding of the fundamental workings of the universe. Fast radio bursts, or FRBs, are intense, millisecond-long bursts of radio waves. They were first discovered in 2007 and have since become one of the most intriguing mysteries in astrophysics. The origin of FRBs remains largely unknown, but they are believed to come from extragalactic sources, potentially billions of light-years away. Their extreme brightness and short duration suggest they are produced by highly energetic processes. Several theories have been proposed to explain FRBs, including the collapse of neutron stars, mergers of compact objects, and activities related to magnetars, which are neutron stars with extremely strong magnetic fields. One of the key challenges in studying FRBs is their transient nature. They appear and disappear in a fraction of a second, making them difficult to detect and localize with traditional radio telescopes. Recent advancements in radio astronomy, such as the development of dedicated instruments like SHIME and the Australian Square-Kilometry Array Pathfinder, have significantly increased the number of detected FRBs. These observatories can scan large portions of the sky, improving the chances of catching these elusive signals. Some FRBs have been observed to repeat, providing crucial clues about their origins. Repeating FRBs allow astronomers to study them more closely and over longer periods, helping to pinpoint their sources and understand their mechanisms. The first repeating FRB, known as FRB 121102, was traced to a dwarf galaxy over 3 billion light-years away. This discovery suggested that at least some FRBs are associated with persistent, active environments like those found around young neutron stars or black holes. FRBs can be used as cosmic probes. The radio waves travel through intergalactic space, interacting with matter along the way. By studying these interactions, astronomers can learn about the density and composition of the intergalactic medium. The dispersion measure of an FRB, which indicates how much the signal has been spread out by interactions with electrons, can provide information about the amount of matter it has passed through. This helps to estimate distances and map out the distribution of matter in the universe. Polarization studies of FRBs reveal information about the magnetic fields they encounter. The Faraday rotation of the signal, caused by magnetic fields, can give insights into the magnetic environment near the source and along the line of sight. FRBs also have potential applications in studying dark matter. If FRBs pass through regions with high concentrations of dark matter, their signals could be affected in ways that help scientists understand the nature and distribution of dark matter. The mysterious nature of FRBs has led to a wide range of theoretical models. These include cataclysmic events like supernovae or gamma-ray bursts, as well as more exotic scenarios involving extraterrestrial technology. Continued observations and detections of FRBs are essential for solving the mystery of their origins. As more data is collected, patterns may emerge that help to distinguish between different theoretical models. International collaboration among radio observatories is crucial for advancing our understanding of FRBs. By sharing data and resources, scientists can maximize the potential for new discoveries and insights. Fast radio bursts are a prime example of how new astronomical phenomena can challenge our understanding of the universe. They remind us that the cosmos is full of surprises, and each new discovery has the potential to revolutionize our knowledge of the fundamental processes at work in the universe. Cosmic background anomalies are intriguing deviations in the uniformity of the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe, providing a snapshot of the cosmos when it was just 380,000 years old. One of the most well-known anomalies is the cold spot. Discovered in the WMAP data and confirmed by the Planck satellite, this region is unusually cold compared to the surrounding areas, suggesting a potential supervoid or other unexplained phenomena. Another anomaly is the alignment of the quadrupole and octopole moments of the CMB. These low multipole moments appear to be aligned in a way that suggests a preferred direction in space, which contradicts the cosmological principle of isotropy. The hemispherical power asymmetry is another puzzling feature. The CMB shows a difference in temperature fluctuations between the northern and southern hemispheres of the sky, implying a large-scale asymmetry that challenges standard cosmological models. Anomalies in the CMB polarization data have also been observed. These include unexpected patterns in the E-mode and B-mode polarizations, which provide clues about the early universe's density fluctuations and gravitational waves. Next, some scientists suggest that these anomalies could be hints of new physics beyond the standard model of cosmology. Possibilities include primordial magnetic fields, topological defects like cosmic strings, or features from the inflationary period. The integrated Sachs-Wolf effect is another area where anomalies have been noted. This effect occurs when the CMB photons pass through potential wells created by large-scale structures, leading to temperature fluctuations. Discrepancies in these fluctuations could indicate new physics or errors in our understanding of large-scale structures. The dark flow anomaly suggests that galaxy clusters are moving in a direction not predicted by the standard model of cosmology. This could indicate the influence of structures beyond the observable universe, or modifications to our understanding of gravity. The lack of large-angle correlations in the CMB is another anomaly. Theoretically, there should be significant correlations at large angular scales, but observations show a lack of these correlations, raising questions about the early universe's conditions. The Hubble tension, while not directly related to the CMB, is an anomaly in cosmic background measurements. It refers to the discrepancy between the locally measured expansion rate of the universe and the rate inferred from CMB observations, suggesting new physics or measurement issues. Some anomalies could be statistical flukes, resulting from random fluctuations in the CMB data. However, the persistence and consistency of these anomalies across different observations and experiments suggest they may have deeper implications. Future missions, like the Simons Observatory and the CMB-S4 project, aim to provide more precise measurements of the CMB. These observations could help resolve current anomalies or uncover new ones, leading to a better understanding of the universe. Researchers also explore cross-correlating CMB data with other cosmological observations such as galaxy surveys and gravitational lensing maps. These combined analyses can provide a more comprehensive picture of the anomalies and their possible explanations. Understanding cosmic background anomalies is crucial for refining our cosmological models. These anomalies challenge our current theories and drive the search for new physics that could explain the fundamental workings of the universe. The study of cosmic background anomalies exemplifies the dynamic nature of cosmology. Each anomaly represents a potential clue to a deeper understanding of the universe, reminding us that there is still much to learn about the cosmos and its origins. Theories of cosmic fate explore how the universe might end. One prominent theory is the Big Freeze, also known as the heat death. In this scenario, the universe continues to expand indefinitely, causing galaxies, stars, and eventually atoms to spread further apart. As the universe expands, star formation will slow down and eventually cease. Existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will cool and fade away. In the distant future, black holes will dominate the universe. They will slowly evaporate through Hawking radiation, a process that takes an incredibly long time. After all black holes have evaporated, the universe will consist mostly of low-energy photons and particles. Another theory is the Big Crunch. This scenario posits that the expansion of the universe will eventually reverse, leading to a collapse. All matter and energy would be pulled back into an increasingly dense and hot state, potentially resulting in a singularity or a new Big Bang. The fate of the universe in the Big Crunch depends on the amount of dark energy and its properties. If dark energy decreases over time, gravitational forces could overcome expansion, causing the universe to contract. The Big Rip is a more dramatic scenario, where the expansion of the universe accelerates to the point where it tears apart galaxies, stars, planets, and even atoms. This theory depends on a specific type of dark energy known as phantom energy, which increases in strength over time. In the Big Rip, the universe's expansion rate would continue to grow until it becomes infinite in a finite amount of time. This catastrophic end would occur billions of years from now, with cosmic structures disintegrating in the final moments. Theories also consider the possibility of a cyclic universe. In this model, the universe undergoes a series of expansions and contractions, known as Big Bangs and Big Crunches. Each cycle ends with a collapse that leads to a new expansion. A cyclic universe avoids the issues of a singular beginning or end, proposing instead that the universe has no beginning or end in time. This model requires specific conditions for matter, energy, and the laws of physics to repeat the cycles. Another idea is the multiverse theory, suggesting our universe is just one of many. Different universes could have different physical laws and constants. The fate of our universe might be linked to the properties and interactions within this larger multiverse. The concept of cosmic inflation also impacts theories of cosmic fate. Inflation posits a rapid expansion of the universe shortly after the Big Bang. Some theories suggest that inflation continues in parts of the universe, creating bubble universes with their own fates. The holographic principle is a theoretical framework proposing that all the information within our universe can be described on a lower dimensional boundary. This idea could lead to new insights into the nature of the universe and its eventual fate. Quantum mechanics also plays a role in cosmic fate theories. Quantum effects could prevent singularities or alter the behavior of dark energy, leading to different end scenarios than those predicted by classical physics. Advances in observational technology and theoretical physics continue to refine our understanding of cosmic fate. Data from telescopes, particle accelerators, and space missions help test these theories, bringing us closer to understanding the ultimate destiny of the universe. The study of cosmic fate not only reveals the potential end scenarios for the universe, but also deepens our understanding of fundamental physics and the nature of reality. As we explore these theories, we uncover more about the universe's past, present, and future. The Big Freeze, also known as the heat death, is a scenario where the universe continues to expand forever. In this model, the universe gradually cools as it expands, leading to a state where all thermodynamic energy is evenly distributed. Star formation will cease because the necessary gas for new stars will be exhausted. Existing stars will eventually burn out, leaving behind white dwarfs, neutron stars, and black holes. Over immense timescales, even these remnants will cool and become inactive. Galaxies will drift apart, and the night sky will grow darker as more stars move beyond the observable horizon. The universe will be filled with cold, dark, and diffuse matter, with no significant sources of heat or light. As black holes dominate the universe, they will slowly evaporate due to Hawking radiation. This process takes an extremely long time, but ultimately, even black holes will disappear, leaving a nearly empty universe. In the Big Freeze, the universe reaches a state of maximum entropy, where no further work can be extracted from any energy source. This marks the end of any significant physical processes, leading to a dark, cold, and lifeless cosmos. The Big Crunch is an alternative scenario where the universe's expansion eventually reverses. This happens if the gravitational attraction of all the matter in the universe overcomes the repulsive force of dark energy. As the universe contracts, galaxies will move closer together, and the density of matter will increase. Temperatures will rise as the universe compresses, eventually leading to conditions similar to those of the Big Bang. Stars and galaxies will collide and merge, creating massive black holes. These black holes will eventually merge, leading to a single, extremely dense point, potentially resulting in a singularity. The final moments of the Big Crunch could see the entire universe collapse into this singularity, a point of infinite density and temperature. Some theories suggest this could lead to a new Big Bang, starting the cycle of expansion and contraction anew. The Big Rip is a more violent end to the universe, driven by a form of dark energy that grows stronger over time. This scenario depends on a specific type of dark energy known as phantom energy, which has a repulsive force that increases without bound. In the Big Rip, the expansion of the universe accelerates to such an extent that it eventually overcomes all other forces, including gravity and electromagnetism. This process begins by tearing apart galaxy clusters, then galaxies, stars, planets, and eventually atoms. The timeline for the Big Rip involves cosmic structures disintegrating one by one. Galaxies are torn apart first, followed by solar systems and individual stars. Finally, the fabric of space-time itself is ripped apart at the atomic level. This catastrophic end would result in the universe being torn apart in a finite amount of time, leading to a complete and utter dissolution of all matter and energy. The Big Rip represents the ultimate fate, where even the fundamental particles are destroyed. Each of these scenarios, Big Freeze, Big Crunch, and Big Rip, offers a different vision of the universe's fate. The actual outcome depends on the nature of dark energy and the total density of the universe. Ongoing observations and theoretical research aim to determine which of these scenarios is most likely. By studying the properties of dark energy and the expansion rate of the universe, scientists hope to uncover clues about the universe's ultimate destiny. Understanding these potential fates helps us grasp the long-term evolution of the cosmos. It also highlights the profound impact of fundamental forces and constants on the universe's past, present, and future. As we learn more, we refine our picture of the ultimate fate of everything. Dark energy plays a crucial role in determining the future of the universe. It is a mysterious force that drives the accelerated expansion of the cosmos, and its properties will shape the ultimate fate of everything. If dark energy remains constant, as suggested by the cosmological constant model, the universe will continue to expand at an accelerating rate. This scenario leads to the Big Freeze, where galaxies drift apart, stars burn out, and the universe becomes a cold, dark, and empty place. The nature of dark energy could change over time. If it decreases, gravitational forces might eventually dominate, leading to a deceleration of the expansion and potentially a Big Crunch, where the universe collapses back into a high-density state. Alternatively, if dark energy increases, it could lead to the Big Rip. In this scenario, the repulsive force of dark energy grows stronger, eventually tearing apart galaxies, stars, planets, and even atomic particles, resulting in a complete disintegration of all matter. Understanding dark energy is one of the biggest challenges in cosmology. It makes up about 70% of the universe's total energy content, yet its nature remains largely unknown. Observations and theoretical models are essential to uncover its secrets. Current observations, such as those from the cosmic microwave background and supernovae, support the idea of a cosmological constant. However, more data is needed to confirm this model or reveal variations in dark energy's behavior over time. Future missions, like the Euclid satellite and the James Webb Space Telescope, will provide more precise measurements of dark energy. These observations aim to track the expansion of the universe with greater accuracy, shedding light on its long-term behavior. The role of dark energy is also linked to the geometry of the universe. If dark energy remains constant, the universe will continue to expand in a flat or open geometry. Changes in dark energy could alter this geometry, influencing the universe's expansion dynamics. Dark energy affects not just the expansion rate, but also the formation of cosmic structures. It influences the growth of galaxies and clusters, determining how matter clumps together over time. The interplay between dark energy and dark matter is crucial. Dark matter provides the gravitational pull needed for structure formation, while dark energy drives expansion. Understanding their relationship helps explain the large-scale structure of the universe. The study of dark energy also involves testing fundamental theories of physics. Modifications to general relativity or the introduction of new fields could provide alternative explanations for dark energy and its effects. Quantum field theory and string theory offer potential insights into dark energy. These advanced theories attempt to unify all forces of nature and might reveal deeper connections between dark energy, dark matter, and the fabric of space-time. Dark energy's influence extends to the fate of black holes. In an ever-expanding universe, black holes will eventually evaporate through Hawking radiation, contributing to the gradual cooling and dimming of the cosmos. The long-term future of the universe, driven by dark energy, raises profound philosophical questions about existence and the ultimate fate of all matter and energy. These questions inspire ongoing research and exploration. As we continue to study dark energy, we refine our understanding of the universe's past, present, and future. The role of dark energy in shaping cosmic destiny underscores the interconnectedness of all cosmic phenomena and the fundamental forces that govern them. Exploring dark energy is a journey at the frontier of science. Each discovery brings us closer to understanding the true nature of the universe and its ultimate fate, revealing the profound impact of this mysterious force on the cosmos. Dark energy has profound implications for cosmology and physics. Its discovery has challenged our understanding of the universe and forced us to rethink fundamental concepts. One major implication is the need to understand the true nature of dark energy, whether it is a cosmological constant, a dynamic field, or something else entirely. This will redefine our understanding of the forces that shape the universe. The existence of dark energy implies that our current models of gravity, based on general relativity, might be incomplete. We may need new theories or modifications to existing ones to fully explain dark energy's effects. Dark energy also affects the fate of the universe. Depending on its properties, it could lead to the Big Freeze, Big Crunch, or Big Rip. Understanding dark energy is crucial for predicting the ultimate destiny of the cosmos. In cosmology, dark energy influences the formation and evolution of large-scale structures. It affects how galaxies and clusters of galaxies form and evolve over time, impacting our understanding of cosmic history. The study of dark energy can also provide insights into the early universe. Observations of the cosmic microwave background and large-scale structure can reveal how dark energy has influenced the universe from its earliest moments. Dark energy research intersects with particle physics. Understanding its properties might require new particles or fields beyond the standard model of particle physics, leading to potential breakthroughs in both fields. Quantum field theory offers potential explanations for dark energy. Ideas like vacuum energy and quantum fluctuations could be related to dark energy, suggesting deep connections between cosmology and quantum mechanics. String theory, which aims to unify all fundamental forces, might also provide insights into dark energy. It proposes extra dimensions and new forms of matter and energy that could help explain dark energy's nature. The discovery of dark energy has prompted new observational efforts. Missions like Euclid and the James Webb Space Telescope aim to measure the expansion of the universe with unprecedented precision, providing crucial data on dark energy. Dark energy's influence on the geometry of the universe is another key implication. It affects whether the universe is open, closed, or flat, which in turn influences cosmic evolution and the potential for a multiverse. The study of dark energy also has implications for fundamental physics. It challenges our understanding of space-time, energy, and the fundamental laws that govern the cosmos. The relationship between dark energy and dark matter is a significant area of research. Understanding how these two components interact could reveal new physics and deepen our understanding of the universe's composition. The implications of dark energy extend to the search for a unified theory of everything. A complete understanding of dark energy could be a crucial piece of the puzzle in unifying gravity with the other fundamental forces. Finally, the exploration of dark energy underscores the importance of interdisciplinary research in advancing our understanding of the universe. Collaboration between cosmologists, physicists, and astronomers is essential for unraveling the mysteries of dark energy and its profound implications for science. In this comprehensive exploration, we delved into the fascinating history of the universe, tracing its origins from the Big Bang through to its potential ultimate fate. We began by examining the initial conditions of the universe, the inflation period, and the formation of fundamental particles, laying the groundwork for the cosmos as we know it. We then discussed the early universe timeline, covering primordial nucleosynthesis and the formation of hydrogen and helium. We explored the crucial role of neutrons and protons and the abundance of light elements. This led to an understanding of the transition to a transparent universe during the recombination era and the emergence of the cosmic microwave background, a critical piece of evidence for our cosmological models. Our journey continued with an in-depth look at the formation and evolution of galaxies, from the first population 3 stars to the complex structures we observe today. We covered the types of galaxies, their interactions, and the large-scale structures they form, such as the cosmic web and galactic clusters. This provided a detailed view of how matter is organized on the grandest scales. We also delved into the mysterious components of the universe, such as dark matter and dark energy. We discussed their discovery, evidence, and the profound impact they have on cosmic evolution. Theories and models of dark matter and dark energy were explored, along with their implications for the universe's structure and ultimate fate. Next, we highlighted key phenomena like quasars, gamma-ray bursts, and gravitational waves, each shedding light on extreme processes and providing insights into the universe's most energetic events. These observations are crucial for testing our theories and understanding the dynamic and violent aspects of cosmic evolution. We also covered the role of advanced observational techniques and computer simulations in modern astrophysics. These tools allow scientists to model complex processes and make precise observations, deepening our understanding of the cosmos and pushing the boundaries of our knowledge. Finally, we discussed the possible futures of the universe, including the Big Freeze, Big Crunch, and Big Rip, shaped largely by the enigmatic force of dark energy. Each scenario offers a different vision of cosmic fate, driven by the properties and behavior of dark energy. Thank you for joining us on this journey through the universe's past, present, and future. If you enjoyed this video, please like and subscribe to our channel for more content. Be sure to check out our other videos, where we explore various aspects of astronomy, physics, and the wonders of the cosmos.